Okay, back with the osdev here. Been a little bit, but that's okay. I have converted everything to C, well, for the most part. I still have a couple assembly files, the Bootsector, the second stage bootloader, the fileTable and testfont. I'm probably going to leave those as assembly for now, for the foreseeable future. I had issues trying to convert the bootloader specifically into C, just with inline assembly and things. I couldn't really get structs to work right and everything to work with inline assembly. So that's not, that's not converted to C. The Bootsector I changed a little bit, but I'll show that in a second. The fileTable and testfont are really just bytes in a file, so those could be changed to be like a shell script or really anything that'll just output binary bytes to a file. Those don't necessarily have to be assembly files. The makefile is a bit different. You'll see I have linker scripts here for our main C files, and I'll probably keep doing that for future C files that are in this source folder. So other than that, nothing, too far changed. Just kind of tried to fix a few bugs here and there. Tried to simplify a little bit, although this isn't as extensive a refactor as I wanted to do. This could still be improved a lot, as you'll see. All the assembly.inc, the include files, have been changed to C header files pretty much. I can show the build process first. I'm in the build folder here, so I'll show the make file. So this is new. This stuff's been changed. I went and learned make a bit. This could probably still be simplified and better laid out, but that's what we got so far. I'm using Clang on OpenBSD for all my C compilations. Could use GCC, but it comes with Clang, so I like the error messages a little bit better with Clang still, so I'm going to use that. Assuming it's the C17 standard, just to have the latest thing, but this doesn't really matter for what I'm doing right now. It's pretty basic C. 32-bit compilation target, aiming for i386 as a microarchitecture. It's going to be freestanding environment, no standard library, no standard include files from the compiler or the linker, hopefully. So I have no built-in for that reason as well. So I don't want to include anything. No standard int, no string.h, no standard IO. I'm doing everything, without pre-built libraries or nothing. No standard include as well. So that should just go with these things. So I should not be including anything. Although there were some hiccups with that. It still tried to include like mem copy and other mem functions when I was compiling, so I had to change. I could not like initialize a full array to 0 or it would make it call to mem copy. I don't have a mem copy set up in my own standard library or anything yet, so I had to change that to kind of fill everything with zeros instead of being able to pre-initialize like a full array with zeros. Could not do that. Anyway, O0 was a little bit weird. O of S and O of Z were misbehaving. I had like strings being cut off or just not working in different parts. So optimization level 1 or whatever that stands for. That seems to work all right. I'll keep this going. Setting the C files right now. The only pure C files I have are the kernel, the editor, and the calculator. The assembly files I still have are Bootsector, second stage bootloader, fileTable, testfont. Source directory from this build folder is, relative path to source, bin directory is bin. Temp files, I'm just using this for bin files. These are make variables, all these. But these are all the final files that are going to be concatenated into the final os.bin binary. So bin files is just taking all of these in order in the list. It's taking all those files and it's prefixing them with ... bin, and then kind of suffixing them with .bin. So I'm taking all these, I'm adding the bin folder to the front and the .bin extension to the end, just so I can get a list of those, and then I cat them all here when I'm done compiling the assembly and C files. Taking, padding it with zeros, making an empty file of zeros, and then taking this temp.bin, putting it into the os.bin and not truncating so it keeps it. And then removing the binaries other than the os.bin. So that's the same as it was before. This just looks a bit different. But okay, to make the OS and to run this, it goes through the assembly files and the C files, which is nice that you can include them like this for the targets and the prerequisites. That's pretty cool. So assembly files are these. For each one of those, I'm just running fasm on the assembly file, which is located in the source directory. So this $@ represents this target, which represents all of these. So some indirection here. So it's going through each one of these, looking in the source file for the .asm, running fasm on it, and putting it in the bin directory as this file name with the .bin extension. So turning the .asm into the .bin in the other folder. Okay, in the C files, I'm running, Clang on it, the cc, doing a -c to run the assembler and everything, but not the linker just yet. Running the C flags for.c, the output is going to be the target name. So the output is going to be this file name, .o, putting it into the source directory, well, taking from the source directory where it's a .c. I'm running the linker explicitly with the linker script on that .o, changing it into a binary with O format binary into the final .bin. Okay, then I'm removing the .o and I'm padding out the .o file or the .bin file. I'm padding out the .bin file to the next sort of sector boundary. So if it takes up 512 bytes, it'll take up 1024. It'll add another sector, I think, or it'll just go to the next sector. Maybe it'll add 0. I forget how I did this. But I'm adding up to the next sector boundary because before in the plain assembly file, you can do like times 1024 minus $, defined by 0 to pad it out. I didn't find an easy way to do that in C or an inline assembly. So I'm padding it out with dd command explicitly here, doing a little bit of math. So I'm getting the file size of the binary that we made with the linker. I'm subtracting file size modulo 512. So I'm taking the remainder of division by 512, and then I'm adding 512, and I'm subtracting that. So that gets the next boundary. So if it was like, I don't know, 800, and I wanted to go to 1024, it'd be 800 minus, you know, modulo 512, and then it would add 512. It would end up adding 224 is what this would do. So then I'm echoing it out. I'm just saying it's this many hex sectors before I'm adding the size, and then it's this many hex sectors after I'm adding this extra size. So you'll see that in the final, you know, make output. And that size that I need to get to the next 512 byte sector boundary, I'm just adding it with dd. So I'm adding zeros to the final target.bin file. I'm seeking to the end of the current file size, so I'm adding it to the end in 1 byte increments. And the number of bytes I'm adding is that size we just got to get to the next 512 bytes. And then I'm moving the bin to the bin directory. So hopefully that makes sense. Run is the same thing. You know, clean is similar to how it was before. I can run make so you can see the example output. It runs the assembler and it goes through the C files and links them. We get the stat line all in one line here. But I'm printing this out just because I still have to change the file size, like in the fileTable or the Bootsector. So I wanted to see this in here so I didn't have to calculate things. It would just tell me directly. But see, the kernel started as 6,360 bytes, which equates to about 12 sectors. And then I added to the next boundary 6656, which is now 13 sectors. So the final file size I need for the kernel in the fileTable or in the Bootsector when I'm loading the kernel is going to be this D, or 13 sectors. And I do the same thing for the editor down here, 12 to 13 in hex, and the calculator. There it is, 5 to 6. Hard to read, a lot of stuff. But yeah, that is basically the build system. But I'll show the linker scripts here. I had to learn, you know, basics about linking and stuff. So this isn't great, but this is what I got to where it works so far. I'm explicitly adding sections to the text section that are going to be first. So the main, like the normal main function in your C, and kernel, instead of main, I have kernel main. In editor, I have editor main. Calculator, I have calculator main. Those I want to be my entry points. But to set an explicit entry point, I found for me the easiest way was just to make another section. So I guess I can show that here. So in calculator, kernel, and editor, I'm adding attribute section kernel entry for the kernel. Calculator has, I think, calc entry. Editor has editor entry. And, you know, void. But if I want this to run first, if I want this to be the entry point, for me, I found the easiest way was to make an explicit section. So the kernel entry section, and then in the linker script, I'm linking that section before the rest of the text section. And I'm starting text at 2000, in this case for the kernel, because we jumped to 2000 at the end of the bootloader to jump to the kernel and execute it. So if I put this explicit section directly at 2000, that's loaded first, and then this is executed as normal from this sort of main entry point that I made. And then for this, I had to put in RO data and BSS for, I think BSS is uninitialized data, so not 0, but if I just do like this token's 50, I think goes in the BSS section. Read-only is read-only data. Data would be data. There are more sections here. These are just ones I set up in the linker script explicitly to follow the text section. So, but that ended up working, and that's all right. I have similar things for the editor and the calculator. It's just I set them at 10,000 because right now I'm loading programs from the kernel at 10,000. So I'm setting them explicitly to 10,000. And again, yeah, the attribute section, editor entry and calc entry. That's how I'm doing that. That's how I'm linking them up. But okay, I can start going through the other ones. I think I showed the build stuff. I will have a more extensive C standard lib going forward. Right now I only have a couple type defs and a standard int file. Just to get things rocking and rolling, you know. So these I'm using in my other C files just to have my standard, you know, my uint8, 16, 32, 64, which we can call and use. But I'm setting them up as type defs just to have available because I want to be explicit. I could use int and character and unsigned long and things, but I want it to be explicit so it made more sense and it's more, hopefully more portable or more easy to make sense of. This thing is exactly 1 byte because it's a uint8, you know, stuff like that. So standard int, pretty easy. I'll add more stuff here. Yeah, I put clang wouldn't let me compile without memset because it craps itself. Yeah. This is pretty easy though. If you want a uint8 of your own, you can say, okay, an unsigned character is technically on this architecture, on my machine, it's going to be 8 bits. So explicitly 1 byte. And the character is assigned 1 byte, unsigned short or 16 bits. Ints are 32 bits because I'm on a 32-bit OS and architecture in this VM. And 64 would be a long. I guess, I mean, I could just go down like here, right? Would that not be too confusing? I'll just do that. I'll go down the list. It's easier for me to keep track. So file ops. So yeah, all the C header. I don't know if I need pragma once. I just put it there to hopefully get rid of some errors when I'm compiling. I don't know if I really need that, but I put it there anyway. That would be the same as doing like, I think if not define, well, I need like a hash, don't I? Whatever, if not defined, like file ops or whatever, and then you put all the code in the file and then you do like define or endif or something. I don't remember how that worked because I've not dealt with this stuff in a large project before, but anyway, I'm doing pragma once. This is just the forward declaration because I have the other function down at the bottom before this is called, so. But I still have the same delete file, rename file, load file, save file as we had before. They're just kind of in a C version now. This probably isn't the best way to do header files. Usually people have like a .h and a .c for the implementation. I just did it all as one to make it easier for me. I had one include file, so I just made it one header file. So I figured that was a little simpler conceptually, so that's what I'm doing. But this should work similar to the other assembly files. I'm just using inline assembly like you see down here, but delete file, you know, variable setup. So I'm saving my drive number here. I guess I will have to beat around the bush a bit with source files. Yeah. So before I change this a little bit, I'll go over this in a bit, but the Bootsector, I'm storing the drive number at a global location just to make it easier, so I don't have to pass it around in DL everywhere. I just store it in one location in memory and just retrieve from that location later on. It's easier. I'll end up giving these things actually meaningful names later. Right now they're just magic numbers, unfortunately. So the drive number is 1 byte at hex 1500. A character pointer basically to hex 1500, and then I'm dereferencing that pointer to get the 8 bits of data at this address. So I found that was a good way to get stuff in C. And it kind of makes sense. I'm saying, hey, there's supposed to be 8 bits of data at this address, unsigned, and then I'm getting that 8 bits of data by dereferencing. Error return codes, although I don't know if I'm still using return code down here. Not in delete file, I'm not, so I don't need that. This is file table size in start sector, so I didn't want to have to pass in other data. So basically I'm kind of dynamically getting where the file table is in each of these functions that I need it. So I'm checking the file name, you know, like it's similar to how it was before, but I'm basically seeing if the file name file table is in the file table. And if it is, I'm getting how big it is and where it starts. And then I'm loading from that. So the file size and start sector for the file table, I'm doing that. The length of this name is 10. Again, that's a magic number, but that's basically the length of this, which is file table. Length of our file names are hard-coded to 10 for now. Check file name returns a file pointer. Let me just pull this up. So I can just show this down here, which my face is probably in the way. That's unfortunate. Let's do that. That looks a little bit better. So check file name returns a character pointer. So I'm using that to be a file pointer to the location of where the file is in the file table. So but it takes in a file name to check for and the length of that, which is, you know, going to be 10 right now. The file table is still at 1000 in memory. So here again, I'm setting a character pointer to 1000. That's going to be our file pointer I'm setting up here. So while there is data at the file pointer, pretty much, I'm checking for the file name, so we're going up to the file name length, which is going to be 10. If the character at the file name matches, the fileTable character, what we're looking for, if that matches at the end, we found it. Otherwise, we're going to go to the next entry. So add 16. Each fileTable entry is 16 bytes, so I'm adding to the next one. Just to show, in case you forgot, because I forget a lot. Well, I didn't really want to do what I just did. So each one of these entries is 16 bytes. So if I'm checking for the name fileTable, it's going to start here. It's going to check, the names up to the length of the file name. If it's not there, fileTable pointer will add 16 to point to the start of the next name. 16, 16. So if we're looking for fileTable, it would find it here because it'll check all of these. It'll match the file name, and we'll break, and effectively the file pointer will be pointing to this F if we're checking for this name. If it goes through everything, it's kind of pointing beyond here, which will be just a bunch of zeros. Okay, I'm back. Had to leave for a while, but okay. So yeah, it either finds the file in the fileTable or it's pointing to 0. So I'm going to go back and go basically down the list from delete file here. We'll get the file size, starting sector. Then we're going to check for the actual file. If we don't find it, then the file pointer's pointing to the end of the file list, it's pointing to 0, so we just return. I'll probably change the return values from these from 1 to 0 and opposite so that I can do if statements better, because right now I'm checking on return from like delete file, I'm checking if delete file equals 0, and I really just want to check if delete file, which this would have to be 0, I think, instead of 1. But anyway, that's something I can refactor later. But yeah, if the file exists that we want to delete, we're going to get the starting sector and file size because the file pointer will point to that entry in the fileTable. Then I'm going to write zeros to there, so just blanking out the thing in the fileTable. The name's going to be free space. So the character at free space is going to be put into the file pointer. So right now this will overwrite the name, the first 10 spaces there. Guess I didn't need to take that off, did I? It'll overwrite the first 10 spaces, at the file pointer for the name. Then it'll overwrite the type here with blanks. Then we're going to put 0 for each of these things. Directory entry, starting sector, file size. So it would say free space, spaces for the extension, and then all zeros. Okay, and then yeah, I want to get the actual size, not just assume 1 sector, but right now we're just assuming 1 sector for all these files. Okay, so doing some inline assembly here in C, assembly volatile, so that hopefully the compiler doesn't change anything. And so far so good, I think, with this, but I'm taking the drive number that we got from the global location, 1500 hex, anding it with 0f, oring it with A0. So anding with 0f to get the head number and the load nibble, and then oring with A0 for the primary drive, which is going to be A0. B0 would be secondary drive. So I'm putting that into, if you don't know inline assembly, this is, the code you want to run. This can be multiple lines like I have here. At the end of the whole, all the statements you want to do. After the first colon, we're doing extended assembly. After the first colon is going to be input, it's going to be output parameters, or things you want to output after it's run. And then the second colon here is input parameters. So these things I want to be kind of initialized or set to these values before this statement is run. So if I'm writing out a byte from AL to DX, I think I had to put the 2% signs for this to work, but the A here specifically, there are some sort of things you can do to hardcode registers or values, or you can make it general memory or in some immediate value and things. But here I'm hard coding register values to make a little bit more sense. This A would correspond to AX, or I think since we're in 32-bit, compiling for 32-bit, it's EAX, but it'll use AL here, so it's okay. So in AX, pretty much, we're going to put the drive number anded with 0F. And then into DX, we're going to put the head drive number port 1F6. So this will write out the byte in AL to DX. This is AT&T syntax. You can use Intel syntax with inline assembly, but I wanted to learn AT&T syntax since it comes up now and then. I might change this later to be Intel syntax because I like it more. It's, to me, easier to read and more succinct and everything. But right now, this is all AT&T. But we're sending basically the drive number to the head drive number port. We're sending this number of sectors to read to the sector count port. So the fileTable size is in hex sectors. We're going to write that out to 1F2, which is the sector number or the sector count port. 1F3 is the sector number port. So I'm sending the sector that we want to start writing at. Okay, I'm sending zeros for cylinder low and high. Later, these probably might have to change. I just don't have that many files in our file table for this to matter right now. But when size limits come into play, we'll have to, increase this from 0 to 1 or 2, whatever, later on. And I'm not doing logical block addressing or anything yet. Later, I probably want to do that as well. But for now, cylinder low and high are just set to 0, 1F4, 1F5. And then we're writing out the command to the command port, which is 1F7. In DX, the command is hex 30 for write with read try. Before we start writing, we want to make sure the hardware is ready to write too. So I have a little while loop here, infinite loop. I'm reading in the byte at data port 1F7 in DX, reading that into AL. And this is output and extended assembly. So input is DX, output, the equals means it's going to be overwritten. So the memory location that's going into AX is going to be a test byte variable I have up here, which is just uint8, so a character. I'm putting that into AL, or I'm pointing AL to that, but after this is done running, I'm reading the byte from DX into AL. Test byte will be overwritten with the value that is in AX. So I'm overwriting this value and putting it into here for the output. And then I'm testing if the busy bit is clear, which is bit 7, 0 based. Bit 7, so you can check by shifting 1 left 7 bits, checking if that's set or not, if it's a 1 or not. I'm doing exclamation marks, that means it's not set. If this was set, we would just check for that, but I'm checking if it's a 0, then the busy bit is clear, we can break out of the loop. If it's still set, I want to keep reading until the busy bit is clear. Because I was reading in, I think on osdev wiki again, for the ATA PIO ports, that if that's set, checking the other bits or values doesn't really matter. So I want to make sure that's clear. And that seemed to fix up some bugs I was having. AL was usually, I think, like 58. My code wasn't going on if I was checking, I think, bit 3 to check if the output buffer was clear, or input buffer, rather. But checking for the busy bit is clear is like universal and it works. So okay, then I have some more inline assembly. You can probably make this work with regular labels, like a label name, although you might have to do the prefix, but I was having some issues with that, so I found doing just like the numbers. I don't like how it reads. It's harder to read loop 1 backwards to this one label, but it worked, so I'm going with it for now. But this is just a label, writing out string word, so writing basically words, not bytes, I guess. I could put words. Write words from DSSI into the DX port, and I'm setting up the input values here. I'm setting a little delay, just like the assembly that we used to have, set a little delay after each string word, and then I'm going back until they're all set. So loop, CX will be 0, it'll go on. Okay, so for the starting values, the input to this assembly, I want to be set before the assembly runs. I'm setting SI with a capital S. I think it's ESI, but SI is being set to the address we want to write from, which is 1000 in hex, because at this point we're just writing the file table with the changed entry because we just deleted a file. CX, lowercase c, is set to the number of words for one sector because we're using outstring word. If this was outstring byte, this would be 512. If it was outstring double word, it'd be 128, Okay, DX I'm setting to the data port 1F0, so writing out from DSSI into the port at DX. After this I read, I think I had this before anyway, but I read sending the cache flush command was good, just in case. So I'm sending that right after, writing out the byte E7 to port 1F7 for a cache flush. And then the actual file, to blank it out on the disk, I'm just using an arbitrary location of hex 20,000 to write nulls to, or zeros to. So setting the file pointer to that location, and then basically 1 to 512 or 0 to 511, whatever, times whatever the file size is. So however many bytes we have in our file, if it's like 3 hex sectors, it'll be 3 times 512, right? We're just filling all that with zeros. So offsetting from the file pointer, just filling it all with zeros, and then I'm writing that to the disk down here. Same thing we did before for the head and drive number. Here the file size and starting sector are the values we got for the actual file on the disk up here. Still zeros for cylinder low and high, still writing write with retry. I might not have to do like these 3 things again and this again, since those are the same as before, so maybe I can get rid of those. But right now I'm just, doing all the same thing. Still reading until it's clear. The busy bits, and then doing this again, the exact same thing, except SI is set to 20,000 because that's where we wrote the nulls to up here. And CX is set to the file size times 256, so the number of words for the file size. So it'll write that many words do a little delay, you know, from 20,000 to 1F0 to get the right space on the disk. And then sending cache flush again after it's all done. Then I'm assuming it's a success because it got here. I'm not checking for errors yet, and I should be, but that'll be later on, hopefully. Enough rambling, I'll go on to load file. Doing the same initial setup for variables here, drive number, error return code, although checking for file name. This one we don't have to check for the file table since I'm just loading a file from the file table. I'm assuming it's there. Okay, get file type and variable to pass back. So I'm getting the extension because I need the extension for some things depending on what's calling this. If it's a text or a bin file, I want to do different processing. So I'm sending it back here. That is an input parameter. So that's the final input parameter here. File name length. Okay, the address that I want to load to is what this is going to be. So from the editor, it's going to be like 10,000, I think. And from the kernel, I think it's at 8,000 still, although maybe that changed. But anyway, yeah, where I want to load it to, I have it as a full double word value. And then the file extension, I'm going to pass back within this variable. So I passed in a character pointer to put the extension at, which should only be 3 length, but I don't have it as a 3. And then I'm filling out the extension here because I'm assuming we're pointing to the file table entry after we call check file name. So plus 10 because it's offset into 10. Since the extension is at byte 10 within the entry, I'm doing 10 plus I 3 times to fill out the extension here. Okay, assuming we're going to return successfully, we're getting the actual file size and starting sector, bytes 14 to 15 in the file table entry. And like above, getting the drive number, setting the file size and starting sector, setting 00 and doing 20 for the command port this time for read with retry, as opposed to write with retry, which is hex 30. For every hex sector in the file size is kind of what this is doing. So for each sector, I'm going to read it in, right? So after reading one sector, or before reading one sector as well, I want to wait until the busy bit is clear. So same as before, check if bit 7 is set by reading in 1F7 into the test byte. Then I'm going to read double words for one sector by doing repeat in string long, setting EDI with the capital D to the address that we want to read into, setting CX to 128 because that's one sector is 512 bytes divided by 4 for double words, so 128 double words for one sector, and then D is the data port, so reading this many double words from this port into the address at EDI. So after one sector, I wanted to do the 400 nanosecond delay to make sure it's set up for the next sector, whatever else we want to do. So I'm reading the alternate status register just because it won't affect the regular one. So 4 times for 400 nanosecond assumed delay. Reading in a byte from alternate status register here in DX 3F6 into AL, which I'm just setting to 0. I needed to set a value for it, I think, because I use double % signs, but maybe I don't. But I just put it anyway. This value is a throwaway. It doesn't matter. And then we're doing that for the number of file sizes in sectors. So if this is 13 sectors, file size is going to be 13. We're going to run this basically 13 times. So that's the shortest one. Okay, rename file. We have file 1, the length of the name. I should have made this file name length, I guess 1, but that's the length of the file name for file 1. File 2, the length of the name for file 2. Again, getting the drive number, setting these things up. Checking for the file name for file table inside the file table, getting the start sector and size for that, and then getting the actual one if it was found. Okay, so when we rename a file, we're basically writing the file table again. So when we're pointing to the name of the file that we want to replace in the file table, I'm overriding that with 10 blanks first to blank out the name, and then I'm writing the second name over those 10 blanks. So I'm writing with blanks and then I'm overriding that space, just so it's padded with blanks in case we don't have a full 10 length name for some reason. Okay, and then again, similar to the above, getting the drive number, starting sector and file size for the file table, because that's what we're writing. Zeros for cylinder load high, write with retries hex 30. Wait until the busy bit is clear, and then writing again from 1000, which is where the file table's at, to the data port at 1F0, 256 words, so out string word, put a little delay and loop back till we're done. Then I'm sending the cache flush command after it's written. So that's not bad. Then we'll have save file, should be the last function here we have to go over in this file. We have the file name, the file extension, we have the file size and hex sectors, and we'll have the address that we want to save from. So file name length, size, starting sector, file table size, start sector, last save sector, free space file name, file table file name, file pointer. I could also use constants here, I think. Like these could be better off being constants. I'll mess with that after. I got it to where it worked and no more. So again, checking for the file table in the file table, getting its start sector and file size, and checking for the actual file we want to save. Okay, so if we found it, then we're gonna go here. So I don't have anything set up for if a file exists already. So if we find the file, we'll have to like overwrite the current file, right? I'm not doing that yet. If we don't find the file, it's a new file. We're gonna check for free space. If the word free space is in the file table, then we have a space we can write to, assuming it's big enough, which right now it's, I guess, 1 sector minimum, so it should be. But I'll have to change that later to find a space that's big enough. But anyway, if the word free space is there, we have free space to write to. If it's not there, then we're just going to be pointing to the end of the file table. We can write a new file at the end. So that's what this handles. But assuming we have a space to write to, which we should, I'm getting the sector before then, so we know where to write to, which is the starting sector and file size that we're adding together to get the last save sector. So if we're writing to the end of the file table, I'm moving back to the start of the last one and saying, hey, we need to add these two values to get the next value that we can write at on the disk. So since the editor starts at here and takes up this much space, we need to move at least this much space after this point to be able to write something to here and not overwrite anything else. So that's why I'm adding these two together. I'm making a new file table wherever we're pointing, so filling out the file name, assuming we're at the end, like after editor, or if we're at a free space point, I'm writing the file name. These 10 characters, adding 10. I could probably make this like ++, and then I wouldn't need that line. That would probably work, but I'm going to keep it like it is because it was working. Okay, anyway, then I'm writing the extension after that 10 characters, then moving past that, and then I need to write the directory entries can be 0. The last save sector, this is where we want to start. So if we take 1D plus 13 in hex, that's where we want to start writing the new file. So that'll be written there. And then the file size, however big the file is, which right now I think these are all going to be 1, but that's fine for any new files, but that's fine. So the drive number, file table, since we're writing the file table entry first, we use the file table size and starting sector. And we check for the busy bit being clear. Again, same as before, we're writing 256 words to 1F0 port from address 1000 for the file table, sending the cache flush after that's done. Then after the cache flush, I'm waiting until the busy bit is clear to write the next data we're going to write. And I'm going to write our actual new file data to the disk. So, these are all the same, but the file data here is what was passed in as parameters in file size. That's how much data we want to write to the disk. That was the parm up here. And we want to write it to that address, which I have down here in ESI, but in file size, the last save sector, since we calculated that, we know where to write it to, starting here. Wait until the busy bit's clear first again. And then we're going to write the file size times 256 for the number of words that it takes up to that command port from the address that was passed in as a parm. So we want to save it from the passed in address on the end. Okay, then we're going to send the cache flush command after all that's done writing, and wait until the busy bit's clear. I'm not sure I have to do this here, but I had it there for some reason, so I'll leave it there. Okay, and then yeah, we have the check file name, which I think I went over already, so that's good. So that was file ops. So I guess I'll look at get key next. Take some water first. Yeah, we're returning the ASCII character in AL from reading data port 60, which is a keyboard PS2 controller. Okay. This file's not that big, under 100 lines, so our scancode to ASCII lookup table looks a little different. I am using constant here, so I know I can use that sometimes. Okay, this is how it was laid out before. It's just to put sort of multi-line string constants in C. I had to do it like this. Hex bytes you can put in, hex bytes you can put in with the /x for hex, and then the values. So these are 1 byte, hex bytes, hex 0, and then hex 1b. Then the number row, hex 8 for backspace, 0 for, I forget, something after backspace, escape maybe, something like that. The first row on the keyboard, D and 1D, second row on the keyboard, third row on the keyboard, etc. Ending with a space, which is what this is. Alternatively, I could put a /x20. And then here, the number row shifts, so this could be a constant probably, but it's not for some reason. If you press shift on the number row, I want to offset from this to get the right symbol. I have left shift, left control, scan code, input character, test byte, old key. All right, so kind of similar to the assembly code, except instead of key and old key, I only need old key. So I didn't need the extra variable there, so I got rid of it. But I'm setting old key equal to scancode by default, which this is going to be set to 0 when this is called, but that's fine. So I found if I tried to do this in C by just reading from the data port at 60, that's all I was doing in the assembly version, right? If I tried to just do that in C, it was just giving me like the maximum amount of characters from the data port. I would read, but there would still be keys left on the data port. If I press like T, it would give me like a bajillion T's. So I only want like one at a time. Unless the user has the keys set down, then it'll repeat, but I only want to return 1 T, not like 1,000 T's. So I found from reading the osdev wiki again, of course, for the PS2 controller page, I think, that if you read the status register until the output buffer is full, so kind of pulling the status register here, then that prevented it. This would only send a key back. This would only read in when there's data to read in, instead of reading like garbage or whatever was previously there. So until I put in hardware interrupt support for this, this works pretty well for now. But I'm reading the status register, which is hex 64, reading that into AL here. So you don't have to use DX all the time. You can put a regular immediate byte with the $ hex 64, reading in to AL, overriding test byte with that value. If the first bit is set, so if bit 0 is the output buffer status from the status register byte, if bit 0 is set, it's full, we want to go on. If it's not set, then there's no data to read yet, so we want to keep reading until there is data. The user presses a key. But if it is full, there's data to read, so then we go on and read that byte of data from the data port, which is hex 60, into AL, and I'm overriding scancode with that value. So I'm getting the scancode the user pressed here. So if this was the last key they pressed, we want to keep going, which if it's the first key they pressed, since it's set to 0, it'll probably go on anyway. But anyway, the left shift make code is 2A, the break code's AA. So if they press left shift, we want to set it on. If they released it, we'll set it off. If they press control, we'll set it on, released it, set it off. Otherwise, any generic break code is going to be bit 7 set, so I can AND it with 1 shift left 7. I also thought about ANDing it with like 80, which is the same thing. That's 128 or bit 7, which is going to be set. But for me, it made more conceptual sense at the time to just write this, saying, hey, I got, 7 bits to the left means bit 7. That made more sense, but you can do it either way. Else if it's above 53, we're at the end of the table delete key. So we don't want to count anything above hex 53 offset from this because we don't have values for that. So I'm just disregarding those. So I'm getting the character they entered. If they did not press left shift, then we're done. We have the character they entered. It'll be like a lowercase a or a number or something. They did not press the shift key. If they did press the left shift key, we want to get what character they did to, shift it. So if they pressed if they pressed an ASCII, a letter A through Z, we want to get the uppercase A through Z. So you can do that by just subtracting 20 in hex or 32, because the lowercase and uppercase letters are that much, they're exactly 32 away. Lowercase a is 32 away from uppercase A. If it's a number, then I'm subtracting 48 in decimal or hex 30 first to convert it to an integer, because ASCII 0 starts at hex 30, so subtract it to get the integer equivalent of 0. And then I'm offsetting into num-row shifts. So if they pressed 1, we're going to offset 1 into this string, and it'll be the exclamation. If they press 0, it'll be the right paren. If they press 3, it'll be the pound sign, stuff like that. Okay, and then we're breaking out of the loop. Otherwise, maybe they press something else. The only special characters right now I'm handling are plus and question mark for shift keys. So if they press shift equal, we're going to put the plus key. We're going to return that to the user. If they did shift and / we're going to return the question mark. Okay, and I also set up a sort of, I probably will go over this before the video is over, but I set up memory a bit different. I have it written down. I just haven't shown it. But I set up a sort of, on paper, a memory map that I have at this point. And it was easier for me than trying to transfer everything into registers and keep that going in inline assembly in C or passing variables back and forth. Just set a global generic memory location to stick values in. So for here, I'm using 1600 as the base and then offsetting from that for keyboard stuff. Getting a character pointer to these locations, and then I'm dereferencing that to set a byte or a character of data at this location. So at 1600, 1 byte at 1600, I'm setting equal to the character that the user entered. This will be the ASCII character. At 1601, I'm setting to the scan code. At 1602, I'm saying the left shift status, so if it's 0 or 1. and then 1603 control 0 or 1. And so inside of like the editor, if I have control S to save a file, I can check if 1603 equals 1, it means they press control. And if the input character is S, then they press control S. So that's sort of an easier way to do that. There's probably a better way though, by using like flags, right? And like ORing stuff together. And then I'm resetting shift and control down here because we don't really need them. We already saved them off. So just resetting those and returning whatever the user entered. That is get key. All right, what do we got? The print stuff. I'm gonna take a slight break because my voice is starting to fade. Okay, let's continue on. Let's look at our good old print functions now. We have print character. This is very similar to print string. It's just I'm doing it once instead of in a loop. So this and print string will be pretty similar, but print character here, taking in the values for the cursor X and Y position on the screen and the character that we want to print. I have some constants here, some 32-bit 4-byte constants for the text colors we want to write. Eventually I want to have some kind of global structure somewhere in memory that has these values, so we're not always doing, you know, blinding Turbo Pascal, Borland, blue and white or whatever. But I have those values here, ARGB constants. So A alpha is 0, R is 1 byte, G is 1 byte, B is 1 byte. So blue is the only one set to FF for blue, and then all E's for right below pure white and RGB. Okay, so I'm also getting a frame buffer here. So in the Bootsector, I'm setting the frame buffer to 9000. In the second stage bootloader, rather, which has not changed at all. So this is the exact same as it was, except I'm writing to 9000. I don't think I was writing to 9000 before. It was 5000, but that I think was being overwritten by other stuff now. So because the kernel gained in size, that's taking over 5000. So I'm writing to a space that's free, 9000. The mode info block info is going to be offset from 9000 wherever I'm using it, which means the frame buffer. And in the mode info block, the double word for the linear frame buffer we're going to write to is going to be 40 bytes offset into the mode info block. 40 byte offset is 28 in hex. Again, I want to give these meaningful names and not magic numbers, but this is how it is right now. So I'm getting the 32 bits, the double word pointer at 928. I'm dereferencing that to get the frame buffer double word value. And then I'm giving a pointer to that for 32 bits. So I'm getting a pointer to the frame buffer value, which is the 32 bytes at 9028. So it looks a little iffy, but that's what it is. Getting a 4-byte value, dereferencing that to get the value we want to point to, and then getting a 4-byte pointer to that value. Because that was confusing to me at first. I was like, what the crap am I doing? But okay. A row and column, I'm just setting to offset into the screen where we want to draw at. So where the cursor positions come into play. So I'm doing cursor-wise the row we're going to write at. For me, my text is 16 lines. So 16, rows on the screen, pixel lines. So I'm multiplying the Y times 16 and times 1920. So this is the number of pixels in one row because I'm doing 1080p. This is the number of rows in a character. So 16 of these pixel rows times the row that we're going to draw at for the cursor. So if the cursor's at row 10, it'll be 10 pixel rows of characters, 10 character rows, which is 16 rows of pixels. And then the column is offset into the line. So since each character is 8 by 16, it's 8 pixels wide. So I'm saying, okay, if we're at column 5, it'll be 5 times 8 for 5 characters over into the line. But you can add these together to offset into the frame buffer location to get where we're actually going to write to, which is what this is doing. And then I have, this is going to be set up to the character we're going to write, and these are going to be if we scroll the screen. So I'm checking for a carriage return or a line feed first off, just in case. So if we have a 0A, it's a line feed. I'm incrementing the row by doing the cursor Y value. If it's above, so this is about the bottom of the screen. So if it's above or equal to there, we want to move down and then go back up. So I'm setting the start point the same way we did the frame up here. Since we want to scroll up one character row, I'm starting this at one row offset into the screen. So one row down is 16 times the number of rows in pixels, which is that. So same as before, we're going to blank out the last row and move everything up. That's what this is doing. Doing the math again, except changing it for 1080p. So this is, 4 bytes, and that many is this many bytes, 7680. And then we multiply it by the number of lines we're going to do, which is -1 character row, which is 16, off from 1080, multiplying that out, and then dividing by 4 for the number of double words or the number of pixels, since each one is 4 bytes. So 0 to there, we're going to set these equal to scroll. Basically, we're setting the original location without the offset to the location with the offset. So it'll take row 1 to screen -1, and it'll move that up. That'll effectively move the screen up. It is a little bit slow because we have a bunch of data now, 1080p. So I probably will put in a back buffer or a second buffer to write to instead of doing this, because we could see artifacts and stuff real easy because it's pretty slow on my virtual setup I got here. But that's okay. Right now this works. So after we do that, we want to blank out the last line. So since start is now pointing to the last line after this, we're just going to set everything on that line equal to the background color, which is going to be, blue. So 0 to 7800, which is the pixels times the character height for the lines, divided by 4 is 7800 double words. So all those pixels in the last line for the character row is going to be text background color. That'll clear out the row. And that's only if we're at the bottom. So if we were at the bottom, we want to move back up to right to the last row that was just cleared. So we're going to decrement Y. So that's only if we're at the bottom. If we're not at the bottom and we got a line feed, we're just going to go down 1 character row, which is again 16 lines of this many pixels. We're going to offset into the frame buffer. And then it's blasphemy, but I'm using a goto because it was easier for nested stuff to go all the way down to the end when we want to stop. So I'm using a label and goto. Oh well, I might refactor to get rid of that later, but I got to put something in to make you cringe, right? So else it's a carriage return, so that's a D. So if they press that, we want to go to the start of the line. So that's whatever X value times the width in characters, which for me is 8 for each character. So cursor X times 8, we're going to subtract that to go to the beginning of the line, and then set this to 0 since we're at the beginning, and then we'll leave. Otherwise it's neither. We want to draw. So to get the character we want to draw, we're going to put a pointer to the start of the memory address for the font, which is at 6000. We're going to multiply by 16 for the height of the character, subtract 16 to get the start of that character because we're going to draw top down. And then we'll get a byte pointer to that because we want to draw kind of like 1 byte at a time for the font. Since it's 16 bytes, we want to start at the first byte, read that, go to the next byte, read that. So to print it, going through each line, 16 is the height, so we're going through each line and each bit and the byte for each line. And if the bit is set, we want to draw the text color. If it's not set, we want the background. So I'm setting the data equal to the offset the line into the character. And if the bit is set, so 1 shift left bit, we're going to read left to right, top down. So 7 is going to be the leftmost. So it would probably help if I showed that right. So let's go to so we're going to start up here. If that bit's set and it's not, we're going to draw background. We're going to go down until we get to one that is set here. So this is bit 0, 1, 2, 3, 4, 5. If that one is set, we're going to draw the text foreground color using the ternary operator there. Otherwise, we'll draw the background color. And then we'll go to the next one. So I could probably put the ++ here and get rid of that, but I'll do that later. And then after we draw 1 line, we want to go down a line. So +1920 to go down 1 line. And then since the character is 8 pixels wide, we want to line up each line of the character. We'll subtract the width. So yeah, eventually I'll replace the 16 with height and 8 with width probably, but not yet. So after we draw 1 character, we want to go and increment the cursor. So I'm going to subtract the height of the character, which is 16 lines of this many pixels. Since we draw a character, we're at the bottom. After we draw the last line, we want to go back to the top to line up the next one. Then we wrote 1 character, we want to go again, next position in the line, we'll increment X, increase or offset into the buffer by this many pixels because that's the width of the character. If we're not at the end of the line, we're done. If we are at the end of the line, we want to do a CRLF, which is going to be, I'm doing the CR first here, but this is the same code as is right here. And then up here, it's the same thing. So, subtracting the width to the buffer and then setting the cursor to the start. Going down 1 row for the line feed. If it's at the end, we want to scroll, so doing the same scrolling code. I could probably make this a function to stop from repeating, but oh well. And then setting it back if it's on the last line. If it's not on the last line, we just go down a character row. Okay, and we return. But yeah, this could be improved as you can see, but that's what I got so far. The string is very similar, so I'll just show that. The only difference being I'm putting a loop here around the whole thing, so don't have to initialize anything. And if I'm taking in a string here at the end, if there is a character there, we're not at the null yet, then I'm going on. So for each character in the string, I'm checking, you know, if it's a line feed, if it's carriage return. If it's not, we're writing the character. So instead of font character, well, instead of just an offset to the character, we're using the byte at the string for the character in the string as the offset into the font. So this is all the same as the other one. And scrolling again. So that's not too bad. The only other thing I want to mention with this is that since we're using 32-bit pointer, it makes it easier since each pixel is 4 bytes for 32 bits per pixel. So you can just increment this, and this will increment 32 bits each time for the pointer. So we're pointing to a 4-byte area. If we increment a frame buffer, it'll point to the next 4-byte area. So that actually makes it a little bit easier. I just wanted to emphasize that. That way we can write easy and just move like by number of pixels here. So this is basically the number of pixels we want to move. And when we write the character, this is, you know, on a pixel basis. That's why I can just set it equal to foreground, background color, and then increment. So it makes it pretty easy. I just wanted to emphasize that. So next, we'll probably go over print file table, hex, and registers. All right, so let's go to print file table. All right, print file table entries to screen. Just taking in the values, well, the addresses, pointers to cursor X and Y where we want to print the file table to the screen. File table name again is file table. Can have a pointer to it. Blanks, file extension, this is 3 blanks. So we want to print it first, so we're going to print string, we're going to print the heading out, you know, all well and good. I'm going to load the file table to memory just in case there were any changes since the last time we called this or wanted to print this. The user could have added a file or renamed something or deleted something. So we'll just get the latest changes here by loading it to memory. I don't think I need to actually cast these values. I was just doing it because I was worried, but this is going to be the length of the file name. This is going to be the address we want to load to. This is going to hold the extension. Although we don't need that in this file, we will need it for other things. So still have to call it with that. File table pointer, we're going to point to where we loaded it, which is going to be 1000. So while we're going to read that, while we are not at the end of the file table, we still have data to read. The first 10 characters of any file table entry are going to be the name. So, you know, we're going to print out Bootsect first, these 10 characters. I'm going to print the character that we read to the screen, and then I'm going to advance the pointer. Then I'm going to print 2 blanks because the heading between the file name and extension, where the file name ends, will have a couple blanks, so it lines up under these heading, you know, sections. So just printing 2 blanks to the screen. File extension bytes are going to be the next 3 bytes. Then we print some more blanks. Going to print the directory entry byte, which, you know, I don't have anything that's not 0, but these are all zeros here. Maybe eventually I will and introduce more fragmentation to this. This is also where we start doing hex values. So I'm going to convert by using print hex. I'm going to print the hex value to the screen, which is going to be a hex word. So I'm not doing double words yet in print hex. It's still 16 bits. So this would be 0x00 would be printed to screen here. The hex number, since I'm using word values, it's 16 bits. So I need to take, well, the character byte at the file table pointer. I'm going to cast that to a 16-bit value before, you know, printing it as a hex value. So it'll be 0x00 for these. So basically I'm casting it to a 16-bit, but we're only taking an 8-bit value. So if that makes sense, these will just be padded with zeros in front until I change it to where, you know, if we ever get up that high, it'll be different. But then we print more blanks for the starting section. We print that value as hex. We get the file size. We print that value as hex. That's all we're doing. It's just printing out, you know, each file table entry. And after that, we print a new line and then go to the next entry. So, but we print a line feed and a carriage return after printing the last byte, and it goes back to the next, you know, till we're done. When we're done reading, this will be a 0 because there won't be any value here. It'll just be nulls that are contained within this sector padding. So that's when we'll stop the loop here, and it will return to caller. Okay, so that's all print fileTable is. So we'll look at print hex because we just did that. Hex string. So this is what's going to be printed to the string. We're going to replace these zeros with actual values if needed. And then we have a lookup table of sorts, just 0 to 15 and hex as ASCII characters. And I'm taking a nibble at a time here. So since we have 4 basically characters that we're going to replace, that's 4 hex nibbles, since 2 of them make up 1 byte. To get each hex nibble, I'm casting the number we passed in as a word to a character, casting as a uint8 and anding with 0f, so we get the lowest nibble there. So if we passed in like 12ab, this would return the b all the way on the end, the least significant 4 bits. Then I'm taking that value and offsetting into this table. So if it's a b, it would be 12, it would go in, 12 into the table, which would be here. B would be 11. Which would offset into here 11, which would return the ASCII B. So this will be the ASCII equivalent of the hex number. And then I'm going to insert it into the hex string by offsetting by 5 minus whatever nibble we're currently on. So I'm starting 0 going to 4. 5 minus 0 is 5. So this will be offsets 1, 2, 3, 4, 5. It'll be on the end. So if we passed in 1, 2, AB, the first one's a B, it would go on the end here. And then we're going to shift the number right by 4. So if it was 1, 2, AV, it would be 0, 1, 2, A. And then we'd get the next nibble. We convert it to ASCII. We put it in the string. We do that 4 times, and then we print out what we got as a string here. Since I capped it off with a null. That's what print string's using as the end of string delimiter. And that prints out a hex value. Pretty simple. Okay, and we print registers. I guess I can show that right quick before I look at print registers. So if we use directory command, we get the string, get the spaces, get the string, spaces, get the hex values here, get the hex values here. Even though they're 1 byte in the file table, again, I'm casting them as 1 word value for print hex right now. So they'll all be, have an extra 2 zeros on the front, but that's okay. But that's what that looks like, and it works. But all right, I'll look at print registers now. The last print function we have so far. Always have to-dos. Got the heading we want to print out, got the string that we're going to replace to print out, have wherever the cursor is on the screen, and have a hex num again for print hex. So we are in 32-bit mode now. I do want to change to using 32-bit values, double words, and also I want to add the flags register. So I have to-dos here. That's all right. First thing I'm going to do is print out the heading. Then I'll print out dx first, even though I could change this to print it out in order. So I should probably do that. Change to print out dx after cx, so all are in order. Okay, but right now dx goes first from when it was the assembly version. So how am I printing out the register values? Well, again, these probably aren't guaranteed to be correct, especially since I'm moving between C and inline assembly. dx will be, whatever the C code decided it should have been when it compiled, but for sake of argument here, let's assume dx is a good value and it's correct. We're going to move the word, so we're moving dx into whatever our first parameter is for inline assembly. You can use %0, 1, 2, and so on to be 0 offset parameters that you want to reference inside your input and output sort of sections for extended inline assembly. So this %0 will correspond with our first thing here and the only thing that we have defined, which is going to be hex num. The equal means we're overriding. The R just means, I think, register. So it could be any register, not just the general purpose ones. But I didn't really care what register we're using for this. All I wanted to do was put the final result of dx into hex num. So any register, we're going to overwrite with the value of dx. And hex num is going to be that overwritten value. And then I'm going to print out whatever the hex number is. So whatever dx is, we're going to print it out to the screen. Then we'll replace the D in the string with an A, because we're going to say, hey, we'll print out the AX register value now. And then I'll print that out. And BX and CX, just replacing, the letters with the register we're doing. Then SI, and the DX is SI, we're moving SI into there. DI, moving DI into there. And then the code segment, the data segment, the extra segment. Going through this fast because it's all copy and paste, and the stack segment. So I do need to add the other values. Also, I do want to change to put, this is just putting what you know, what value is contained within the register. It's not assuming that's an immediate value or an address or anything. So I might change this later to also print out what the register value is and then what value is at that memory. But I'm not sure if that would be useful or not, but I'm thinking maybe I could have that included in the future. It depends. We would need the context or semantics for that, so I'm not sure if I want to do that or not. But anyway, just printing out all those register values. I'm resetting to dx because this wasn't being reset now, since this is sort of a constant memory being a pointer. If we change it, it's going to be changed, so we have to change it back so it's not permanent. And then a new line when I'm done. So that's the register values. So print reg, if I do print reg, it calls print registers, and that prints these out. So these are not really guaranteed to be as correct as they were when this was in assembly, because, you know, after it's compiled with C, it could be using the registers for whatever purpose. I don't know. I'm not being explicit with them now. It's in C. At least I know the stack segments are set up right from the global descriptor table we did in the second stage bootloader. The code segment is set to offset 8 within that global descriptor table. And since we do a far jump to go to 32-bit mode and flush the cache and everything, it is correct. And then the data segment is set to 16, which the other ones are set to as well. So I know those are correct. I probably do want to add like the stack pointer out here in the flags register. So yeah, that would be good for the future. But that is print registers. So okay. So then we can move on to the screen ones here, which aren't too bad. This one's pretty short, as you can see. But to clear the screen, like in the print character and print string functions, I get a pointer to our linear frame buffer that's on the screen, which is 40 bytes into the mode info block that we set up at hex 9000 in the second stage bootloader. So getting the 32 bits there, dereferencing to get the 32 bits, and then getting a pointer to that to get a pointer to the frame buffer, sort of pixel pointer being 4 bytes, 32 bits per pixel. So basically for every pixel on the screen, 1920 by 1080, every pixel on the screen I'm going to set to whatever our background color is. Right now it's hard-coded to just blue. So, you know, every pixel on the screen I'm making blue is all this is doing. And yeah, I'm sorry I didn't show these little small demos in between. I didn't realize that until today. I was like, yeah, that would probably be useful. But, you know, if we print out a bunch of garbage, I can show scrolling too. If you might not believe me, scrolling's a little slow, like this. On my OpenBSD setup in this virtual machine, I do not have simultaneous multi-threading enabled, and it is also not available. So maybe when I installed it in VMware, it didn't give access to that in the kernel or something, because originally this was just emulating a one-core machine, so I don't think it had the capacity to add that as an option to enable, right? So this is running basically all single core if it's slow. And that's also good because I can see if I code anything really badly, I can try to optimize it. And if it works on this, it should work in general, hopefully. So for other people's machines later on. But anyway, we have a bunch of crap on the screen. We clear it, everything turns to blue, and we reset, you know, all the way up there. So, okay, that's how clear screen works. Cursor. I renamed move cursor just to cursor, and I added a remove cursor function as well that I'm using within the editor and other things. So inside cursor, I'm just doing a regular hash define for text, background, foreground, color constants. I gotta do things differently in each one of these files, you know, just to give different perspectives on how to do things. So in another one, I would have had, you know, constant uint32t. Here I'm just doing a define, you know, just to give you different ways to do things, I guess. And because I gotta be difficult and not consistent. But in this, for our move cursor function that we had before, for the C version, I'm taking in the values, not the addresses, but the values of cursor X and Y on the screen. We want to move the cursor to. Again, setting up the frame buffer here. Setting up bytes per scan line, which is a value within the mode info block. It is 16 bytes into it, so at 9010. Yeah, I'm getting a 16-bit pointer, and I'm dereferencing that to get to the 16 bytes that are actually located at this memory address. Okay, and that contains the bytes per scan line value, which for me should be the same as linear bytes per scan line, which I probably should move towards because I'm telling it I'm using a linear frame buffer. This isn't guaranteed to be correct, but that's all right. It is for what we're doing, which is simple 32-bit per pixel 1080p. This is going to be probably 1920 times 4 is what this value is going to be. And I'm really not sure I'm using it in this program at all. So I did at one point, but I'm not now. So, but in the future I might use this, so I'll keep it there. Like print character and print string, I'm using the row and column values and offsetting into the frame buffer to start off. And font character for our font cursor, which is at the end of the font file, which, there we go, took a minute. So this is our font, the cursor in the font. Again, since I'm not using the delete key as an actual character we're going to draw, it's at the end of the ASCII table at 127, I'm just using a line at the bottom to represent our cursor. So a deep underscore, if you will. It's all the way at the bottom of the character. That's what our cursor is effectively. So I'm going to that area within the font, getting the character pointer to, offset into there. At the end of the table, at character 127, height of the font is 16. So for each character, and then I'm subtracting 1 because we're only printing that last line of ones. And yeah, I'm showing that here. I'm going to the end of the character, I guess effectively the character cell on the screen to draw the cursor. I'm going to the last line. Since it's 16 lines high for each character, the last line would be line 15 instead of 16, which would be the start of the next character. So, okay, but this is the same character drawing, thing as we had in print character and print string. It's just checking if the bit is set in the byte. If it is, we're drawing the text color. If not, we're drawing the background color. And then incrementing for the next pixel. So all I'm doing for remove cursor, it's similar to move cursor, except I'm just blanking out the line by default. So I do everything the same, except instead of choosing if we want to draw the text color or the background color, I'm only drawing the background color. So it just overwrites that cursor line of pixels. It just overwrites that line with the background color, and that kind of removes it. And that kind of simplified some logic in the editor and other places where if I type something and then do a backspace or go down a line or something, by default it was keeping the cursor line below where the cursor previously was. So I wanted a way to remove that easily to kind of simplify logic and make it a little bit better for the user. But anyway, that's all that's in the cursor file. So let's look at the hex to ASCII, which is very short. All it does is return the hex character, the number, offset into a sort of lookup table string here, like the print hex had. So I guess I could call this from print hex as well instead of including it in there. But yeah, you just pass it, 0 to 15 value, and it returns the ASCII equivalent. That's all this is doing. So I could probably even do this without needing a separate function, but I just kept it here for completion's sake. It's pretty easy. So, okay, so the other things, bring this up again, would just be the actual source files we're doing. Now, second stage.asm, that's going to be the exact same as it was before, so I'm not going to show that. I didn't make any changes to that file. The Bootsector I did change a little, which I said at the start of this video, I think. Mainly tried to simplify it a little bit, so at the bottom of this file, I added a little subroutine here called load sectors. So because we had the drive number, sending ahead to the drive number port, the cylinder low and high port are always being set to 0. The drive number for my use case right now is always the same. Cylinder low and high are set to 0. The command port, we're just reading within the boot sector. So these are all the same. And then reading a sector at a time. That logic was also always the same. So since it's all the same logic and it was being repeated 4 or 5 times, I just moved it into its own section. So for each thing that we want to load, we're reading from the disk and loading to memory. I'm setting up how many sectors we're going to read, setting it up in BL. Oh, and initially I'm setting ES to 0. So ES equals 0, just to set up sort of ESDI effectively is what I'm doing there. But okay, yeah, I'm setting, however many sectors we want to read here into BL, so number of sectors -1, because I'm checking after I read one sector in the loop. So set it to -1. And then the address we want to read those sectors into. So after I set this up in every section, I'm setting explicitly the number of sectors we want to read and the sector number that we're going to be reading from. Those are the only other variables that are going to change within this. So the second stage bootloader is right now, it's 3 sectors long, so I'm setting BL to 2. I'm reading into 512 bytes after the boot sector, which is at 7C00, so this is at 7E00. The number of sectors to read is 3, and it starts at sector 2, which I have right now, which is where it is in the fileTable right now. Second stage is at sector 2 for 3 sectors. So I have that there. The fileTable is going to be 1 sector, so I just XORed BL. We're reading into 1000 hex for the memory location for the file table, 1 sector long as sector 9 and hex. That's where this is at. So sector 9, 1 sector. So it's pretty easy. You do that and then call load sectors. The kernel is 13, so we do 13 minus 1 into BL because it's D. So 13 long, moving into memory address 2000. We're reading in D number, or 13 number sectors starting at A. In the font, we're reading into 6000. It's 4 sectors starting at sector 5. So forward 5. And then when we jump to the bootloader, you know, I'm just moving the drive number back into DL. I'm storing that into global area again, 1500, just make it easier. And then we're gonna do a far jump to 7E00 to move execution to the second stage bootloader, which was loaded first to 7E00. So jumping there, we'll go and execute it. Okay, so after that, you know, our little load sectors function, setting up the head and drive number, setting that up, writing that byte out to DX after we OR it with A0 and AND it with 0F for the head and the primary drive. Cylinder low and high are being set to 0. And the command port's 1F7, we're sending a 20 there, read with retry, and then polling after 1 sector each time. So sector buffer requires servicing is, I think, what osdev wiki had in some section, but this is equivalent to testing. This is byte 3. This is bit 3, actually. I might change this to test the busy bit, but this has been working so far. When it's ready, we read in a sector's worth of words from the data port into ESDI, which is why I set up ES to 0 first. But we're reading that into ESDI for CX number, which is 256 words. Okay. And I'm setting the 400 nanosecond delay after the 1 sector, reading from the alternate status register 3F6 4 times into AL. And if BL is 0, we've read, you know, the number of sectors we want because we set up BL for the number we want to read each time. Number we want to read -1 rather, because we read one first before checking that. But if we're done, then we're done. If we're not done, decrement for the next section, the next sector. Reset DX to the command port to read the next status register byte to check if it's ready, and then we read in the next sector. You know, it's a loop. After we're done with the loop, we return. I'm not going to go over the table because you've seen that, or the font, because those are just bytes. Those haven't changed other than sizes in the table, but you've seen it, so don't need to go over that. So I guess calculator, editor, and kernel. Okay, so let's go over the C files here. Calculator being the first one. Got the include things about what I need to use in here. Print character, string, and hex. Cursor to move the cursor around, clear the screen, and get a key. All right, these are just forward function declarations here. Guess I'll put that there. Have some constants for error, true and false. I don't think I'm using all of these, but maybe I am. I don't remember. But yeah, these are all global. Have the buffer that we were using before that the user is going to use. Have the scan to get the position within the buffer, the error message, and then the cursor things. I'm thinking now I might make the cursor XY into some other area in global memory. Maybe I'll make like a giant block of like kernel used memory and have structures in there for like the cursor and the keys and everything to keep it more organized. That way I don't have to have separate variables. I can just call from that location in memory, like for the cursor or other things. So I might do that going forward. Just thought of that. But yeah, cursors, and then a number that we're going to use later on for passing around. Called it parse num because I think I'm using it within that function. But anyway, like I showed in the linker scripts, we have the calc entry. So that's the section I'm putting first in the text section to run this as the entry point to this program, this file, when we load it at 10,000 from the kernel. You can call any of these regular main. This name doesn't matter. It's just, if you're doing it like I'm doing it, this is what matters. As long as that's there before the other text sections and the linker, then it's fine. I got an input character. I got our valid input, which is just the numbers, plus, minus, multiply, divide, parentheses for nested expressions, and a space, the enter key or carriage return, and escape, because when they press escape, I'm going to return to the kernel, and that is 1B for the scan code there. Okay, so first off, I clear the screen. Yeah, set the initial cursor position to the top left, 0, 0, and I move the cursor there. All right. So we get the next line of input to parse mathematical expression, hopefully. So just an infinite loop right here. We get a key from the user. We check if it's valid input. So I'm looping through this whole thing, checking if they entered one of these keys pretty much. And if they didn't, then it's invalid, and we get the next key. If they did enter in a valid key, we check if it's enter or not. If it's enter, and they didn't enter in anything yet, then we're gonna go on. But if they did enter something, we're gonna go and parse what they entered and hopefully evaluate a correct expression. Yeah, scan has to be above 0, which happens when they enter a key in. Okay, or the buffer is full and we evaluate what they have, but it won't necessarily be correct, it's just they entered in a lot of stuff. When it comes back from evaluating, we're clearing the buffer for the next line of input, so I'm just setting all 80 characters of the buffer to 0, and continuing the loop to get the next key. So simple enough. If they press the escape key, then we're going to return to the caller. If they didn't press escape and they didn't press enter, hopefully it's a valid character by this point, it should be. We're going to store it within the buffer at the current scan position, which starts at 0, so the first character is going to be what they entered, and we'll increment scan for the next, thing. So this is, I'm using it as an index, so it's not a great word for an index here, but it makes more sense later. And then we're going to print what they entered to screen, so just print the character and then move the cursor, one character over. Okay, but when we actually go to parse the buffer and start the expression, going to print a new line for the next line of input. If we ultimately get an error, I'm going to print the error message to the screen. Otherwise, I'll print the final answer we get from evaluating the expression. I'll put that to the screen, and then we print a new line for the next stuff. And then that'll return up here after we parse the buffer, clear it, and go on. Okay, but if we're going to parse it, call parse sum first. And again, we're using... Well, I based it off this Bacchus-Naur form, simple grammar for a somewhat recursive descent parser is kind of what this is for a calculator, basic 4-function calculator. So we start off by parsing the sum, which then we call product, which then we call term, which ultimately should end up in a number. But if not, sum can also be itself, evaluated from a number plus a product, which eventually will evaluate to a number. So a number plus a number can be a sum, or a number minus a number can be a sum. For a product, you can have a number times a number, or a number divided by a number. And for a term, we can have a negative number or a nested expression, which is a parenthesis, and then we start over with the sum again, and another parentheses, or just a number itself. So this should handle negative numbers as well, but I haven't tested that too much. But anyway, when we go to do the sum and, checking if it's the product, if it's an error, we return an error. If we get a number there, skip blanks. If we're adding, it'll find a plus, we'll get the next number, we'll add them together. If it's a minus, we'll get the next number, add them together. If there's an error anywhere in there, we'll return error. It should go back up here after we go to parse sum eventually. It'll propagate back up. If we eventually get an error, we print the error message. So that does eventually work. There's just a lot of error words on the screen here. But num calls parse product calls parse term. And again, if there's an error, we'll go back and propagate that back. If there's not an error, we're checking if they're multiplying, get the next number, multiply them together. Otherwise, divide them. And in each one of these, I'm pretty much returning the number that we ultimately end up with to pass it back up the function call stack. So if we added or subtracted, that'll eventually return the number. Multiply or divide will eventually return a number. Assuming they typed it in correctly. Parse term, we're seeing if they entered in a nested expression. So if it's between parentheses, we go back to parse num again to get or parse sum again to see if it's a sum or a product or a number. If they didn't close a parentheses, it's unbalanced, that's an error, so I'm returning an error for that. If it's a negative number, and they had a unary minus, then we're taking a negative of parse term. So we ultimately return the number and just paste a negative right there on front. If it's none of those, if it's not a number, a negative number, not a nested expression, then we return an error, otherwise we return the number that was entered. So, and that happens right here with the call to parse number. But okay, and in each of these I'm calling skip blanks between the operators that you did, so in the operands. So if you wanted to put blanks in white space, you can. Only blanks though, only spaces, not tabs. I should probably expand this to do tabs as well. So while we have a space, we just skip the space pretty much. That's what match character does, reads it and goes on. Parse number, I'm checking if there's a digit, if the number we pass in. That's why I'm using parse num up here, to have this kind of be global so I don't have to pass this around everywhere. It's not the best way of doing it, but it kind of works. But if we find a digit, while it is a digit, we're going to keep getting it. When we're done getting the full digit, we'll return it. Otherwise, there's an error, it was not a true number. So is digit. accepting the pointer to the num, basically checking if the current position in the buffer that we're evaluating, if it's between 0 and 9 in ASCII, then it's a digit. So we're going to multiply it by 10 and add the next numeric representation of that, which is subtracting the ASCII 0. So if they entered in an ASCII 3, subtracting the ASCII 0 would equal integer 3. That converts, the ASCII to int. And whatever number we currently have, we'll multiply by 0 to get the next tens place. So if they entered in something like 32, num would start out as 0. So 0 times 10 is 0. But then we'd add in the 3, so it would equal 3. And then the next go around, we'd multiply it by 10 to get 30, and then we'd add the 2. So if they entered in ASCII 32, after 2 calls to this, it would evaluate the integer 32. We'd eventually return it. So we'd return true, this would return the number, and it would go back up the stack, Okay, but if there's not a number in anywhere they did not enter in ASCII 0 to 9, then it's an error. We'll return false, which ends up returning an error from parse number. Okay, and the last thing here, match character. If what we're checking for is the current character in the buffer that we're evaluating, then it's true, otherwise it's false. So if you put like 1 plus 2, and we're checking for a plus up here in parse sum, and we're on the plus, if it matches, then it'll return true, so we're good. We'll go on to get the next number. If it's not a plus, we check the minus, that just passes it down to see what character we entered if it's correct for whatever expression we're evaluating. If not, then it's false. We get an error. It propagates back up. We print the error. So I just had a separate thing for a new line here. It just prints the line feed and carriage return, move down, moves cursor. Okay, I'm back. I realized I didn't have well, not that I need to show, but I didn't show any sort of demo for the calculator, so I just wanted to get that started here, just in case people were wondering, they hadn't seen it before. If we pull it up, there isn't anything here currently. I want to write like text at the bottom saying like allowed operations, add, subtract, multiply, divide, nested expressions and stuff. But right now, I also want to make a print integer function to go along with the print hex, which I don't have right now. Everything's just in hex, but type a number, it returns, the hexadecimal representation of it because I'm just typing that in. We can do, minus, so this will be 17. We can do plus, that'll be 22. We can do multiply, that'll be 20, 16 and 4. Yeah, and we can do divide. If we do 20 divided by 4, that should be 5. So we can do that. We should also be able to do nested expressions. 10 plus 2 plus 3, so that should be 15, which is F. But depending on the order of parentheses, it's not really going to be great. So if you want things to be super explicit, you'll want to double up. I'll do minus 3, and we'll do times 2. So hopefully this gives 18, and it does, okay. But just to be doubly sure, it will evaluate left to right pretty much, but depending on the order you do the parentheses in, you won't get the same answer. If I doubled the parentheses over here, it would be different. But anyway, that's just a little calculator demo. It works through somewhat arbitrary nesting. And it won't do the whole number. If I do this, it'll probably crash or fail, or it'll just put 0. Interesting. I did see one thing I wanted to change in here, and that is to remove the cursor after we type something in and press enter. So I could do that right quick, I guess. So before we parse the buffer, let's do remove cursor. And I think it's calc cursor X and calc cursor Y. I believe, right? Yeah. All right, so let's just remove the cursor first. Expression or buffer, whatever. Let's just see what that does, because I didn't want it to show up there and remain. Everything's good, compiled and assembled. Okay, so only thing is I have to keep pressing Alt and moving the window every time, but that's all right. So if we do this before, the cursor remained after you press enter, and now it disappears. See on the top line there where the 10 is, before there was a cursor, now it disappears. It's a very small thing, but I think it adds up to, it looks a little less janky, a little more professional. That's all, just wanted to do that right quick, but that should be it for calculator. Hopefully I explained it all right last time I was recording. So we'll move on to the editor, which is probably the biggest file, and then the kernel, which, brings stuff together. It's not a script, dummy, you gotta do that. Okay, the editor. So again, C, standard int file, print character string and hex. We have file ops because we're gonna load and save and edit files from the editor. So we got a print file table, cursor, clear screen, get key, hex to ASCII, you know, standard stuff. I have some sort of defines here for constants. End of line, we're saying a line ends at 80 characters. So I have that being 80. Some keyboard scan codes we're taking care of for the editor screens and inside the text editor and the hex editor, you know, left, right, up, down, arrow. These are the scan codes for that, home, in, delete. The keybinds, like when you first pull up the editor, you want to create a file or load a file. So you press C or L for that. If you want to create a binary file or an other, which will be text file, you press B or O, you know. And then in the hex editor, we have run input being $, and program question mark, save program as capital S. So I probably will add or change other things for other editor modes or stuff in the future, but there you go. And then other forward function declarations here outside of main. Global variables. I do want to reduce global variables eventually. I just have not refactored to pass things around yet. But global file name and file type, file size, whatever character we got from the user. Cursor positions, a pointer to the file table or other things. An offset into the file that we're editing or loading. The length of the current line in the file we're on for the text editor. So this is for the length of the file in bytes and lines. A string for entering a name, the current scan code and control key status we have, the current hex count we're on, because when in the hex editor I take in two characters like A and F before I print it to the screen and before I save it to the file, because there's 2 hex nibbles and a byte. So this is just basically a 1 or 2 counter that I use later. Blank line is just a line of blanks to write over stuff, to overwrite with blanks on the screen sometimes. I'll make these constants later, hopefully. So this is where I store the current hex byte before I print it or load it or do things with it. And then the message that appears on the bottom of the screen. Okay. So again, editor entry section for the main editor void, and I use this within, sorry, that's the calculator, I meant the editor. I meant the editor, the linker script for the editor entry. So that's what this section is for. So it's loaded first, so it executes first. Okay, video memory. This is the frame buffer, but I kept it as vidmem for whatever reason. And I'm not using it, so I kind of don't need that. Yeah, so I don't need that there because I'm not using it anyway. All right. These two are written to the bottom of the screen, depending if we're in the hex or text editor. But then, you know, when it first boots up, it says, hey, you want to create a new file or load one that exists. If you're loading a new one or you're creating a new one, you want it to be binary or other. I guess I can show that. You know, create new or load existing. You press C to create new, and it tells you which one, binary or other. Create new binary. You can type in binary stuff. Save it, run the code, turn to the kernel, etc., etc. You load an existing file, you can load a text or hex file. So that's an example of loading the file table. And if we load the Bootsector, then you know there's the Bootsector, which is pretty empty right now. That's all right. Put a to-do there for that. Make string constants. Once I put in memset or memcopy, then I can just, you know, initialize the full array to 0, but I don't have that right now. So to make it compile with Clang, I had to, you know, set things to blank or 0 manually in for loops. So I do this in the kernel as well, but that's how I get around the needing memcopy or memset functions or things. I just manually set them in a for loop. So less efficient, but oh well. Clear the screen initially when we open the editor, then we print the string, which says you want to make a new file or load a current file. Move the cursor there, get the key. So we're going to keep getting a key until we get create new or load current. Yeah, just an infinite loop until they put C or L, then we go there. I could make a thing like take escape here to go back or whatever, which just goes to the kernel, but right now I haven't done that. But if they make a new file, clear the screen again, move the cursor again, have them choose a binary or another type of file by pressing B or O. Reset the bytes, the current file, because we haven't put anything in yet for a new file that they're making. Then we take the B or the O eventually. We clear the screen, set it up again. So the file in memory, it was at 10,000 before, I think, but now it's at 20,000. So just arbitrary location to load and edit a file at. Just memory 20,000 was free, so we can use that. This is the offset into the current file. We're not doing anything with that. The file type, if they chose a binary file, is going to be bin, so we're filling that out and putting the message at the bottom for the keybinds for the hex editor, and then we're going to the hex editor. Otherwise, they're making a text file. We fill out txt, we write the text editor keybinds at the bottom. We fill out a blank sector, which we could do for the bin file as well, but that's all right. We fill out one sector by default with zeros for a new file, because we're assuming it's going to be at least one sector, which it should be. And then just initialize some variables, cursor position, current line, the length of the current line, and then the file length. And then we go to text editor. Okay, if they chose load file, I'm going to a load file function, which is right down here. I guess I don't know the best way of doing this, going back and forth for like what I'm currently talking about. But if we make a new file and it's a text file, you see at the bottom we have, you know, the key binds, Control R, return to kernel, Control S, save file to disk. That's what we went over up there. And then also in the text file, I have the current cursor, X and Y position, and the length of the current line, because that was really useful for debugging, because I fixed some issues with navigating in the text file. So, well, I didn't spell it right. Testing. Oh, I don't have exclamation support. That's okay. But that solved issues with, you know, moving with the arrow keys and home and end and stuff. It was getting really wonky and really bad, but now it works. We get the right, I can go to the end of the line, and we can get the correct length of the line with or without the enter key, and then you should also be able to overwrite and go back, but okay. Editor load file. I have an index for loops, and then I have the editor keybinds, which I don't need these in the main file because I'm not using them up there, so that's something to keep in mind, right? Oh, I am using them, never mind. I could make it global and not call it in two separate places, but oh well, we'll keep this for now. So when you go to load file, it prints the file table to choose a file type. We have the message to choose, we input the name, and then it goes to load it, calling the load file function in the file ops include file. We pass it the name, the length of the name, which shouldn't matter, but I'm casting it for some reason. I don't really need to cast it. Name, the length of the name, up to 10. The address where we're going to load it to, and then the file type, which is 0. And again, I should make this return like a 1 by default or whatever. So I can just check if load file and not if load file equals 0, because that's weird. Because that would be equivalent to if not load file, but we want to check if it does load. So that's a little, yeah, that reads a little bad, but oh well. If it loads, then we break out of this infinite loop. If it doesn't load, then we have an error and we keep entering a file name until we get something to load. That's all that's doing. Guess I can just have this up permanently then, because I keep bringing it up. But we go to load, it prints the file table, we put something in. If we put in garbage, it's going to say there's an error, which I didn't. Let's wait till it does, because it takes in a key after it says load file error at the bottom. Press any key and it, you know, reloads the file table on the screen. But we're like, okay, let's load the file table itself. You have to put it in up to 10 with the spaces. So after I put in a space, it loads automatically. Brings us to the text editor, which has some, you know, some issues with loading the hex, because I don't have, there's hex literals and they're not technically ASCII characters in the file table. So I'll have to work on that in the future, but anyway, that's loading a file, that long digression. All right, if we successfully loaded something, we got to load it to the screen, or well, if they put in a file to load, yeah, and we loaded it successfully. Depending on the file type, we go to the hex or the text editor. If it's a hex editor, then the file type, the 3-length file type string is going to match the ext bin string, which is bin. So if it's bin, then it's a bin file. And we got to load a hex or a binary file. So I'm clearing the screen, resetting the cursor to the top left, setting a file pointer to the file location at 20,000, which is where it was just loaded to. So 512 times, I'm getting the current character at 20,000 where the file was loaded. I'm getting the lowest nibble of the current character. This is for hex file, mind you. I'm ANDing it with 0f to get the lower nibble, converting that to ASCII. So if it's an F, it'll be ASCII F to print to the screen. I'm printing the character we get in ASCII. Then I'm getting the next character and printing that to screen. So I'm just printing, you know, the 2 hex nibbles in each byte to the screen by getting each nibble. 1 by shifting left by 4, and 1 by just ANDing with 0f without shifting left. So this gets, you know, the left nibble, and then this gets the right nibble. And if we're not at the start of the line, we print a space between the hex bytes. If we're at the start of the line, we don't print a space. And then I'm incrementing to get to the next character in the file, and the file size is now 1 byte larger after we print out, you know, the first byte. After we print out all those, get the keybinds at the bottom, reset the hex count, resetting to the start of the file location, and then resetting the offset to the start of the file location as well. Then I'm loading the hex editor. If we're loading a hex file like Bootsector, you know, for each byte in the file. Each byte is 2 hex nibbles, so we're loading the first byte and the second byte is what I was printing out there. You know, converting it to ASCII and printing it out. And then if we're not at the start of the line, I'm printing a space between each byte. If we are at the start of the line, it looks wrong and it's offset wrong if I do print a space, so I'm not printing a space at the start. So that's all, just printing them all out up to 512. Okay. But if they print a text file, or they choose to load a text file to edit, I'm resetting, you know, the cursor length of the line, the file length and lines, and bytes, and resetting the file pointer to the file location because it was loaded at hex 20,000 again. So for each sector, but right now it's just one sector, we're basically printing the file to screen. So if we have a new line, I'm going down one line, but I'm printing a space on the screen first, and I'm going down one row. Because when the user enters in a new line in the text editor, I'm going down, but I'm physically representing it on the screen as a space, so it doesn't look weird. I think Vim, if you show stuff, it's like a dollar sign at the end of the line. I could do something like that later on. Right now I'm not, it's just a space. If it's not a line feed, but it is less than 15, which I need to allow string constants, which I'm not right now. I guess if it's within quotes, I'll change it to do that later. But right now, yeah, if it's basically below 15, then I'm just printing the ASCII equivalent. So if they put in 10, I'm printing an A. Well, actually, if they put in 10, I'm putting a new line. But if they put in 12, I'm going to print like a C to the screen. If we're at the end of the line, we're at 80 characters, then I'm printing a new line. So same thing up here. If the end of the line character is a new line, I'm printing a space. Otherwise, I'm just going down a row for the new line. Okay, if it's not a line feed and it's not below 15, I'm printing the character. You know, if they put in regular text, you know, A through Z or 1 through 9, then print it to the screen. And for each character, technically each byte that's being printed out, going to the next offset in the file, going to the next byte in the file, and incrementing the file length in bytes. So the file length in bytes should be 512, maybe 513 because I'm doing a plus plus. The offset is however far we are into the file, and the file pointer is that byte pointed to in the actual file. So if we're on like byte 10 into the file that we're going to edit, the offset should be 10. The file pointer will be that 10th byte at the memory location. All right, right in the text editor keybinds, I'm resetting to the start of the file. So however many bytes we've gone into the file and loaded, I'm going back to the start by subtracting it from the file pointer. File offset is then 0. So file pointer should be 20,000 at the end of this. But this should be equivalent at this point anyway. And resetting the cursor to the top left, moving it there. So I'm getting the length of the first line to edit. So before we're at a new line character, I guess I should check for end of file as well. But before we're at a new line character and before we're at the end of the file, I'm just going to keep going on till we find the new line or we're at the end of the file. And if assuming we find a new line or the last byte, I'm incrementing the current line length to include that new line. Otherwise it won't be included in the length of the current line. And I'm resetting location to the beginning of the file, going on to the text editor. So what all does this mean? It's all just mumbo jumbo and is useless right now. I'm using it as part of the text editor. So we'll go back. Let's make a new text file. So if I have something like, you know, first line, I meant to do second, but we'll do 23rd end, 23rd end line. Third line. If I have something like this and one line is shorter than the other, when I move the cursor to that line, I want it to go to the end of the shorter line and not stay within its current position. Because if I went to the end of like the third line here and I went up, you know, I want it to go back here and not like out to the right, because that wouldn't be any valid position in the file, and that's not what the user typed in. That's not what was loaded. So I'm using the file length, or well, the current line length to be like this kind of pointer here. So the length len position here is the length of the current line, basically to determine if I need to go outside. Well, this is broken, as you can see. This should not be happening. But other than that, when it was working before, it should go to the length of the shortest line here. But yeah, I got some issues there. See, this one is 9. This one should not be 12, but whatever. I had some issues. Other than some rare issues, usually it kind of works. But alright, the text editor proper, which you saw just right then where it broke, so I have some bugs to fix. I have the keybinds at the bottom. Again, I don't need to put keybinds everywhere, but it is right now. I have a saved cursor X and Y position when I write stuff and want to return to where the user was. So I just have a couple variables to save the cursor position. And I have the strings at the bottom left that you saw for the X, Y, and length. These things are printed out when you're moving around. So draw cursor X and Y in current length before anything else is done. And in between, key presses. So when you're moving around, typing stuff in, this is updated after every key press usually. Saving off the current cursor position, I'm drawing the X, Y, and len strings at the bottom along with their current values. That's what I'm doing here. So cursor X is being set to 1, cursor Y right now is 1 above the last line, which is around line 65. And I'm printing the X and Y, the X string, the X value, incrementing cursor X, the Y string, Y value going after that, and then the length and the length value. Resetting the cursor to the saved values that we saved off. Restoring, I guess, would be better. Restoring the cursor values before we printed these. And moving the cursor there. Okay, then I'm getting a key from the user. And this is where we actually have the input loop starting. From calling getKey, scancode and control key are saved at the end of getKey, so we're just getting those previous values. So whatever was previously entered, we have those, and then the ASCII values and input character. So if they press control and the character they pressed was R, we want to return to the kernel because that's, the keybind we printed at the bottom. If it's S, we want to save the file. So return to the kernel, we just return, and then this propagates back up the call stack and returns to, well, right now we can only call editor from the kernel, so the space in the kernel where the file was loaded and jumped to, it jumps back to that position, which you'll see in a bit when I go over the kernel. But if they did save, what am I doing? Print character again to erase cursor. I could change this to remove cursor. This is one position where I didn't do that, one place. Cursor X and Y values. So before I made the remove cursor function, I was just printing the current character in the file again. So if we're on like an A, then I print the A again just to erase the cursor because it looked a little better when they did save. Otherwise it would leave the cursor position there and it's like, it looks a little jank. But let's just erase the cursor here. And we write the bottom screen message by blanking out the full bottom line and then writing the file name strings, which says enter file name when you go to save. And then the user enters the file name. And we call save file with the file name they entered and the file type, whether it's text or bin right now. I think this is the file size, so just 1 hex sector. And then this is where to save it from, which is 20,000, where the files are being edited and loaded to. If there was an error, we write an error message at the bottom. Otherwise, we save successfully. Right now it can't error as well. I don't have proper error handling in save file, but if it did error, it would, print the message. But if it saves successfully, then we reset the file location to the start. I probably should save this off and restore it to wherever the user was editing instead of resetting to the start of the file. Just thought of that. That seems pretty obvious now in hindsight. Let's do save and restore user's file position instead of resetting to the start every time. So maybe I'll do that eventually. Okay. So that's when we save. Otherwise, we got navigation keys. I guess I can show saving. This is saving for a text file, I think, right? So if we have it, well, I'm pressing Alt, which is not great, but if we have a file here, test line 2, we can move around and stuff. When we save with Control S, Control and then S, it prints the enter file name at the bottom left there, and you enter in the file name. Once it's 10 characters, it goes back to editing from the start of the file. Also right here, it left the cursor and then it erased it, so that's good. I was gonna say it left the cursor, which is a bug, but... And we can go back, assuming it saved correctly since it didn't press the save message. It should be in the file table now. It'll be at the end because there wasn't a previous free space. If there was a free space, it would save over that position. So if we delete something like the calculator, and we have a free space there, and then we go in the editor, we'll save a binary file to be different. It's AF, bin AF. Press Shift S, I should make it Control S to be consistent, but Shift S saves this. This will be test bin 001, sure. Control or question mark to return to the kernel. So wherever the calculator was, we had free space because we deleted it. Save file writes over the free space. I haven't shown that yet, so I'm just showing that now. But okay, that's tangential to the editor. So if we press the left arrow, we want to move the cursor 1 byte left. In this case, we're in the text editor right now, right? Not the bin. Yeah, we're in the text editor. So left arrow in the text editor moves 1 character left, 1 byte left in the file. So if we're not at the start of the line, I'm going to remove the cursor. I'm going to decrement the file pointer to point to the previous byte offset from hex 20,000, where the file is in memory. I'm decrementing the offset as well, and the cursor, and we're moving the cursor one character left pretty much on the screen. Okay, then we're going on to get to the next character. Our right arrow, we want to go one to the right. So if there is still space to move, one to the right is not the current length of the line. I don't need to print the character again. This could be remove cursor, which I think is less code than calling and passing this stuff. So let's remove the cursor first. Actually, that's kind of self-explanatory. It removes the cursor, so I'll just get rid of the comment. All right. And we'll move one to the right in the file, the offset, and, the cursor position. But this needs to be cursor x++, because we just got rid of the other stuff. Printing a character implicitly moves the cursor by 1. So I changed it from print character, so we have to move it ourselves by 1. If they press the up key, we want to go one line up in the file, unless we're on the first line. Move one line up. I should check. Oh yeah, here we go. If we're on the first line, I'm just going on and skipping. If we're not on the first line, we can go at least one line up, so we're going to do so. Move the cursor, decrement Y. We have to find the length of the current line that we're moving up. In case it's shorter, we want to go to the end of the shorter line, not in the same position as the longer line we're on. But we're going to decrement by 1 byte first off before we find the end of the line to get the line length. So the end of the previous line is going to be, we'll have a new line character pretty much, or it'll be the start of the file, one of the two. But assuming we're on at least the second line, there should be a new line. Although this doesn't work if we just type in 80 characters and go on, so this isn't great. Let's put it to do for that. A line feed. So I need to take that into consideration. But assuming we're only doing line feeds for end of lines, we're going to go until we reach the end of line of the first one, or well, the one above where we're at. So I'm going to keep decrementing, going back in the file until we find that. And then I'm going to move past it and increment the length of the current line. Because that line feed at the end of the previous line is the end of that line, what I'm considering to be the end of that line rather. So the text on a line and the line feed before we go to the next one is going to be all part of that line. I'm not including the new line as part of the next line because that's jank. Like here in Vim, the end of the line is after this E, even though you don't see it. But the line feed for that is counted as this line. If we found the line above the one we're currently at, we need to get the length of that line. Yeah, we need to count the number of characters in the line above the one we're at until we reach the line above that one, or the start of the file. If that makes sense. So we need a new line above the previous new line, or the start of the file, which would be offset 0. So until we reach one of those two conditions, I keep decrementing and incrementing the length of the line. But again, like this, that could be position 80, not necessarily a line feed. So I'll put the to do there as well. But if we found a new line, then we found the start of the previous line, we're moving past it. So if we found the previous line, which starts at a new line, if we found a new line before the previous line, that's the end of the line before the one we're moving up to. So we don't want to count this new line because it's the start of the previous line. We just want the first previous line, so we move past this new line. I'm explaining this terribly, but I can't. Maybe I should draw a graphic here to make more sense. I might not do that though. If we reach the start of the file, the offset we're in will be 0. Because I couldn't think of a good way to check if the file pointer was pointing to hex 20,000. If the offset is 0, then we're at the beginning of the file. And if I didn't increment the line length here, then it was not including it. So off by 1 errors are very common in C. So there you go, include the first byte. So the whole reason of getting the line length was to see if the line was shorter. If it is shorter, so if it's less than wherever the cursor position is, the line length is 1 based, the cursor is 0 based, so I have to add 1 to accurately compare. But if the line length is shorter than where the cursor is, I'm moving the cursor to the end of the shorter line. That's what this is doing. And then wherever the cursor is, since the file pointer and offset are pointing to the start of this line, I need to move into the line to wherever the cursor is. If it's at the beginning, it'll be 0, these won't move. But if we're in the middle of the line at character 5 or something, then the file pointer will point to that, wherever the cursor is. Okay, and then we move the cursor to the new position on the line above where we're currently at. So that was all for up arrow. So down arrow, we'll be doing something similar, but going down 1 line. If we're at the end of the line, we're at the file length and lines that we calculated from loading or editing so far, and we'll continue because we can't go down 1 line if we're on the last one. It's not going to work. Otherwise, we're going to get rid of the cursor. We're going to go down. Cursor Y is 0 based for the top left, so incrementing Y goes down 1 line on the screen. Setting the current length to 0 because we got to figure that out. We're looking for a new line, but again, do I still have it saved? I do. It could be position 80. But right now, if we find a new line and we're not on the last line of the file, then that's the end of our current line. We're going to move past it. And then we're going to search for either another new line to be the end of the next line or the end of the file. So that's what this is doing. If the offset is not the length, -1, because that's 1 base, we'll put that there, and the line could be position 80. Okay, but if we find the next new line or the end of the file, you know, we got to stop. But until we find those, we've got to keep going on. And since we're past the end of the current line, we can increment the line length until we find this. If we reach the end of the file or the new line, we want to include that as part of the current line we're now on. So I increment this one more time. And then we check again if the line is shorter than the one we're moving from, and this will be before the cursor X position, and we move it, you know, to the end of the shorter line that we're moving to now. So this I'm doing differently, but I'm going to the start of the current line, decrementing the length of the line pretty much, and file pointer and offset are 0 based, so I'm subtracting 1 from the length first, but this moves the file pointer and offset to the start of the line in memory that we're editing. And then I'm moving into the line wherever the cursor is. So I could probably do this minus cursor X, but I broke it out into 2 separate lines here, but that's okay. Going to the start of the line and then offsetting into the line is what that's doing. And moving the cursor, then getting the next key. So home key will go to the beginning of the line, removing the cursor, and just subtracting cursor X from the offset and file data pointer position, and moving the cursor to the start at position 0 for the X value. If they press end, we go to the end of the line, so it should go to 80, but I don't think I'm doing that. Oh yeah, I don't need to go to 80. I just need to go to wherever the end of the line is, which is the length of the line minus the cursor position. If the line is 10 characters long and the cursor is at character 3 into the line, we only need to move another 10 minus 3 or 7 to get to the end of the line. So that's why I'm subtracting X from the line length, adding that to the pointer and offset and the current X position, and moving the cursor there. Okay, if they didn't enter in a navigation key, they put in A through Z, 1 through 9, symbol, whatever. They're putting something in to type to the file. So if they put in, well, if they press the enter key, it'll be D. So we want to do a new line. I'm going to print a space, because visually I want to print a space for the new line. Then we'll print a CRLF, which will move the cursor down into the beginning of the next line. Input character would be a D, so that's carriage return, then A is a line feed. I'm going to put the line feed literal into the file. We're just going to show it visually as a space, but it will be a line feed in the file. And then we're going to, increment the offset. This is a new byte, so we're going to increment the file length, lines, and bytes. And then I'll reset the line length to 0 because we press enter, we're on a new line, although I have to-dos here because if we're editing a previously typed line, we need to move everything down. It's not going to be a new line. So that is a little buggy, but I'm not doing that yet. Okay, if they didn't press an enter key, they did like an A or a T or a 2 or something. If there's no data there in the file yet, this is a new character, a new line, whatever, then, it's a new byte into the file, so I'm incrementing the length and the bytes. I'm putting that character into the file data by dereferencing and then incrementing. And we're at a new offset in the file. Okay. And I'm going to print it to the screen, and I'm going to move the character. But this is assuming insert mode, yeah. If I want to overwrite a character, right now I'm not incrementing the length, but I am putting it into the data, which is fine. So I don't know. I don't think that handles this though, because I would still need to move the rest of the data. So I think I'm assuming overwrite if I'm not, if there is data there, and insert if I'm not, but I'm not really handling those two cases. So I just have a to-do there. Many to-dos. Okay, but that's the text editor. It's not that long. I just take forever to explain things badly. So the hex editor, where we're typing in only hexadecimal bytes. Initialize cursor to the top left. We draw it. We get the keys. Scancode control key, same as before. If they put in to execute, which I think is $sign right now, because it works as sort of a hex monitor. So if you type in valid x86 machine code, you can run that as long as it's up to the 1 sector limit right now. I don't know how well that'll behave. It will have to be 32-bit code now because we're running in 32-bit. So if you type in valid 32-bit machine code up to 512 bytes, you should be able to run it. I just don't know what all you would want to do with that, but you can do that right now. So Maybe you'll have fun breaking your system, I don't know. But if you do want to run the code, again, the file is loaded and being edited at hex 20,000. So I'm just adding the file size to that because that points to the end of the file. I'm putting in a var return at the end of the file. So hopefully, no matter what you run, if it doesn't break anything, it'll return back to the editor. So I'm putting in a var return to hopefully do that. Yeah, I'm resetting to the start of the file, which is at 20,000. Okay, and then I'm getting basically a void pointer to that, and I'm jumping to it. I don't need to do this because I'm doing this a little more succinctly in the kernel, but I think at the time when I read Stack Overflow or whatever, they recommended giving a name to it. So this is a void pointer, or a void function pointer, however you're supposed to say that. That takes in no arguments. And I'm just initializing it to a void pointer function that takes no arguments to hex 20,000. And then I'm calling it, so this will call hex 20,000 and execute whatever code you've written to the current hex file. And then count as 0. After we run it and we return, hopefully, because I put in a var return, after it's executed, it should return to this point. Hopefully. If it doesn't, I don't know. It's probably buggy, but I'm resetting whatever byte you're currently writing. I'm resetting to the start of the file and the offset to the start of the file and the cursor position. So if they didn't want to run and execute, maybe they wanted to go back. They press Ctrl R or whatever I have in the hex. I think it's question mark. Then we're just returning to caller. If they did a save program, which is capital S right now, then I'm removing the cursor first. I'm printing a space here, but I can call remove cursor. We'll do that. Because semantically that makes more sense conceptually. Remove the cursor first and then go to save the program, which I made a separate function. If the user pressed a backspace, because I am handling backspace and delete within the hex editor, but not the text editor yet. But in the hex editor, if you press a backspace, I want to blank out the character you're on and then go back one. So that's what I'm doing. Really, I should take all the file data in front of that character and move it back one as well, because you're kind of like deleting the data there, but I'm not doing that. I'm just writing a space. Same thing for delete. I'm just blanking it out and not moving it back. So that needs to be like to do. All right, delete will do the same thing. It'll just point to it, I think. Yeah, so we'll do that. But if they did press a backspace, the character and the scan code, they're going to be equal, but the character and the scan code I'm returning are going to be 08 for backspace, because that's what it is in the character set. If cursor X is beyond or equal to 3, this is the start of the second hex byte on the screen. Since each hex byte is 2 nibbles, that's 2 characters and a space between each byte. That's 3 overall for each character. So if we're past the first character, we're at least on byte 2, X is going to be at least 3. So that's what this is doing. So if we are at least on the second X byte, I want to blank out that byte, which is 2 spaces to the screen and then moving the cursor back. If we print 2 spaces, that'll be at least 3 plus 2, so it should be 5, I think, by minimum. So yeah, that should be correct. So we blank out, move the cursor back to the start of the previous byte that isn't blanked, make that byte 0 that we just blanked out, and then go to the previous one. So this would probably be better understood visually as well, right? So if we make a bin file, af10, if I press backspace here, well, nothing's going to happen. If I move back to this af and I press a backspace, it's going to blank out the a and the f and go back to the start of the 10. Right? So it prints out 2 spaces, moves the cursor back 5. Delete key is similar. It prints 2 spaces. It just does not move the cursor back. It moves it to the back of this previous byte. It prints 2 and moves back 2. So this 10 would be blanked, but it would stay in the position where the 10 is if I press delete. And that's what it does. And it makes it 0 in the file. If they press the left arrow key, I want to go 1 hex byte back on the screen and in the file. So if we're at least on the second byte, we move it back to the byte before the one we're on. And then we go back 1 byte in the file. Right arrow, if we're not at the end of the line, which here's, I guess, 75. And then we're going to move forward to the next hex byte on screen, which is 3 for 2 nibbles and a space. And then we're going offset into the next byte. Okay, if they press up, we want to go up 1 on the screen. Since this is all hard-coded to be max like 80 characters per line, it's pretty easy. We can just hard code and then move the cursor up by 1 line. We press a down arrow, then we do the same thing, but in reverse. We increment and move down 27 characters into the file. 27 bytes, sorry, into the file. I could be wrong. Let's see, just with the Bootsector. let's see, 1, 2, 3, 4, 4, 5, 6, 7. No, that's 27 hex bytes per line. Never mind. This is probably greater than 27 times 3 is 71. So that's not even 80 long, right? There's 27 hex bytes I'm printing per line right now for the hex editor. So I'm moving up those 27 bytes. If I go up one line, if I'm going down one line, I move forward 27 bytes. And then I'm moving the cursor up or down 1. You know, and left to right, I'm moving by 1 byte. So, sorry if I was confusing. I confuse myself sometimes, a lot of the time. If I press home, we want to go to the start of the line and to the end of the line. So home, since there's 3 bytes between, 3 characters between each hex byte, after removing the cursor, I'm going to go back cursor x divided by 3, because each one will be offset by 3 characters. So divided by 3, we get the number of characters in hex bytes. Number of hex bytes and characters. Would that make more sense? The number of hex bytes and characters into the line, because each one is 3. So we're subtracting that to go to the start. If I go here, where's my cursor at the top? Okay, let's go to the start. Let's press end. End goes to the end, and home goes to home, although it's hard to see. I'm pressing end and home. End is on the 49, home is on the 88. I guess the cursor position at the end is 79. So 79 minus cursor x over 3 goes to the end. Otherwise, just cursor x over 3 subtract to go to the front of the line. I could probably print the x and y values like I am in the text editor. I'm just not doing that for whatever reason. But I might do that later. It would make it easier to see. But that's okay. Since each 1 hex byte is 3 characters visually, the number of bytes to move back is the number of characters divided by 3. That's what this is. Okay, and then end key as in reverse, except we take the end of the line will be at position 79, which is 80, offset from, well, 1 based it would be 80, the cursor is 0 based, so it's 79. Cursor x divided by 3 is the number of bytes, and that's how many we want to offset into the file if we're moving to the end of the line. And then we set x to the end, the start of the ending hex byte, rather, which is 78, because 79 is the last nibble of that byte. We move the cursor there. Okay. So if they didn't press a navigation key, we want to check if the user entered a valid hex digit, which is 0 through F. Could check is digit or is alphanumeric, but just if it's 0 through 9, or capital A through F, or lowercase a through F, then it's valid hex. If it's not, then we go on. That's all that's doing. If it's lowercase a through F, when I'm printing on the screen, I don't have to do this, but I am. Just make it easier. If they print it in lowercase, I'm just converting that to uppercase by subtracting 20 in hex or decimal 32. And we're going to print that capital to screen. So whatever they put in, A through F or 0 through 9, I need to convert it to basically an integer to store it into the file. If they entered in A through F, I'm subtracting hex 37. If they entered in 0 through 9, I'm subtracting hex 30. And this just converts to decimal 10 to 15 or decimal 0 through 9. Then if they entered in 1 or 2 bytes for each nibble, 1 or 2 characters for each nibble, I'm going to increment the hex count. If they entered in 2 nibbles, that's 1 hex byte. So if this is 2, I'm storing each character into the hex byte here by default, right? But if they entered in 2, wherever the first nibble is, I'm going to shift it left by 4 to make room for the next nibble. Then I'm going to OR that byte with the current input character, which has been converted to decimal. So if they put in like 2B, the first one would be a 2. When they enter in the B for the second character, it's going to shift the 2 over and then OR it with the B, so that the hex byte would be 2B, not overwrite the 2 with the B or do B2 or anything. Okay, then I'm setting input character to hex byte and the file pointer to input character. I don't think I need to do this. I could probably just set this to hex byte because that would be equivalent. It might break if I get rid of this, but I'm going to put, is this needed? And I'll look at that later. Okay, and then they entered in a new byte to the file after these 2 nibbles, so we're offsetting 1 byte into the file because we just entered that. We're going to go over to the next byte, resetting the hex count for the next 2 nibbles in the next byte. But if we're not at the start of the line, we want to print a space in between the hex bytes, the 2 nibbles and characters. If we're not at 0, we're at least 3, so print a space. If we're not on nibble number 2, if we just typed in the first nibble, I'm just storing that into hex byte currently. But okay, after that, we're almost at the end of the file, I swear. Right about at the end. So save hex program. I specifically made a thing to save the hex file for some reason. I think it looked a little cleaner if I broke it out into its own function. But again, the hex editor keybinds, I need to find a better place to put this. But I'm basically getting what size the file is and how much more we have to fill out one sector or an additional sector. Right now, the max is 1. But, you know, eventually it'll be more than 1. So I'm dividing the file size that we currently have by 512. And if it's 0, then it can be up to 512. So that's why I'm checking the modulus to get the remainder after division. So if we're at if we filled in 500 bytes, 500 hex bytes out of the maximum allowed right now, which is 512, there will be 12 left over here. So I'm just getting that 12 left over, filling it with 0. Otherwise, we don't have a full sector filled out yet. We don't have anything filled out yet. So we fill out 512 zeros. If we have more than one sector, then I'm checking how much more we have to fill out to reach the next sector, but just by doing the modulo again. But this is the same as this code. And when we're saving, I want to print out, input the file name. So that's what this is doing. It's a bin, it's a bin file type. I'm inputting the file name. We're calling save file with the file name, with the file type, which is bin. The file size right now is a max of 1. Okay. And where to save the file from in memory is hex 20,000. If there was an error, I'm going to print the error message. If it was successful, then I'm going to put the keybinds back at the bottom and reset the cursor to the start of the file. But to do, restore cursor to last user position, not start of file. So these little kind of subroutines, not really full-on functions, but I guess they are technically. When we want to input a file, I'm just taking in 10 characters by calling getKey and putting that into the file name. So 0 to 10, file name's filled out with whatever the user enters, which could be invalid or special characters or stuff, but oh well, I'm not handling that. Okay, fill out bottom editor message and write bottom editor message, or write bottom screen message. They kind of go hand in hand. Whatever message we put to write at the bottom, I'm passing in. So I'm just filling out the bottom message array with that message till it's null, so the full thing here. Then after that, I'm appending the file type. So a couple spaces, a bracket, dot, file type, bracket. And I'm writing that at the bottom by calling this, which just writes a string at cursor x and y of 66. Cursor x of 0, y of 66. So if I'm writing a text file, it'll say .txt, writing or editing. If I'm editing a bin file, it'll say bin. So if I choose to create a bin file, down here at the bottom, it says bin. That's what this is being appended to. Normally it just has the hex editor keybinds, but then I am suffixing or appending the file type right here and then writing the message. So this is y66, that's the line 66 at the bottom. Hopefully that makes sense. If we write a text file or edit a text file, this says .txt. That's all those things. That's all those things are doing. And that is, if you can believe it, we're done finally. That's all it is for editor, which is the longest file I have by far, and I take far longer to attempt to explain it. The last file, at least the last file we're going to look at during this session, is going to be the kernel. So the kernel is not as long as the editor, so fret not. Again, the C standard int that I have, clear screen, print string, print character for printing, cursor.h, get key to get keys, print hex, registers, file ops to save, rename, delete, load files, fileTable needs to be printed when we press the directory command, and hex to ASCII to convert things as needed. So, like the other ones, I have, the kernel entry, which I think I've shown already, but that's okay. I'm loading it at 2000 from the second stage bootloader when I'm jumping to execute it. So at 2000, I have kernel entry, which is this section before the rest of the text, so that this is loaded and executed first. Void kernel main void. Got a bunch of, variables here. Kernel cursor positions, a tokens array, a pointer to the tokens array, tokens length array, pointer to that, the number of tokens we have, a file name 1 and 2, which should be changed to just use the tokens, but I have separate variables for that still. The command string that we're entering right now, it's 255 max. I'll make that 256 actually, 0 to 255. A pointer to the command string, the current user input character, the length of the user input. These are all basically text constants or string constants here for the commands. So you type in CLS, that's the clear screen command. Print reg is the print registers command, so on and so forth. File.bin and text extensions are bin and text. This is a file extension array, 3 characters to hold, bin text or whatever. We have a file pointer to a text file, because if we load a text file right now, I'm printing it out to the screen. This is just a pointer to that file when we go to print it out. Something with wrong, which is the Windows message, Windows error message. Not found string, sector not found string, go back message, press key to go back. I don't know if am I still using that? Go back message, I don't think I am. I'm not. I'm not using it now though, so I'm gonna get rid of it. Some of these things I'm using, so whatever. Like failure, I think I'm using failure. Yeah, I'm using failure at least, just not the other ones. This is the user's prompt. So in Linux, this would be like PS1. Yeah, PS1's for the user, right? So yeah, I think the other one's for root, but program not loaded message, all this stuff. Okay. I need to clean up some of these constants and remove them or change them later, but that'll be later. Like the assembly version, the initial setup, I'm just clearing the screen and printing the boot message. The menu string, welcome to Queso 32-bit C edition. C is in quotes because, you know, I mean, it's C, but it's not the best. So that's why that's in quotes, because I don't take myself seriously enough. So the user input loop, before the user enters in any line of input, I'm clearing out all the relevant arrays and variables. So again, memcopy and memset I don't have implemented. So I got errors when compiling and trying to initialize an array. So I'm just filling them out here. 50 zeros for the tokens array, 5 zeros for the lengths array. Token count is 0, 10 zeros for file name 1 and 2. And then this will be, yeah, 0 to 255 for command string. I'm printing the prompt, which is just, you know, a caret and a colon. Moving the cursor after that. Right now they haven't input anything, so the length is 0. So we got a key loop, which ends, was it down here? Yeah, ends there. So we get a key from the user. If they press enter, we want to run whatever their input was. Technically, this is the shell we're in now. So I remove the cursor and then go break to tokenize their input and run it. If they pressed a backspace, we want to erase the character and go back. So the input length is greater than 0. We're going to go back and put a 0 there. I'm putting a null there, so I'm technically ending the line. This isn't great. Let's do this. Move all input back 1 character or byte after backspace, if applicable. So if they press a backspace in the middle of the line, I want to move everything else back. That's after that. But right now I'm assuming they're only pressing backspace at the end of the line right now. So I'm just moving back by 1 and capping it off with a null. So if we're after the prompt, the X position for the cursor will be at least 2. If it's not, then we're not going to backspace into the cursor because that would cause some bad stuff and bugs. So, but if there is a space to backspace to, I'm decrementing the cursor position, I'm printing 2 spaces, moving back 2 spaces, and moving back. So I think this was to erase the cursor, so I could probably redo this to use remove cursor, but I'm not doing that right now. So I could probably remove the cursor, move it back, print a space, move it back. That might work better, but I'll think about that. Move back 1 space, okay. I'll do that later. And then we get the next character. If they didn't do a backspace, I'm going to store whatever they input into the command string array variable thing. And I'm saying, hey, they entered a character, so the input length goes up by 1, byte counter of input. And I'm also printing what they put in to the screen. Okay, if they pressed, this is after the character loop here, so they press enter, so it broke out of the loop. So if they press enter, but there's nothing there, I'm saying, hey, you didn't press it. Well, it says input or command not found, so technically, yeah, they didn't put in a command or anything. So I'm printing that out and going back. But if they did put something in, I'm capping off their input with a null in case it isn't already. And then I'm going to tokenize what they did. So my really basic white space delimited tokenizer here. I'm setting the pointers up for command string tokens and tokens length, resetting the pointers. Okay, so the token loop, as long as we're not at the null yet in the line of user input, if it's a space, we're just moving past it for white space delimited. And then if it's between 0 and 9, or between capital A through Z, or it's an underscore, or it's lowercase a through Z, that's my valid input. So if it's a valid input, I'm storing that within the tokens array by writing it to the tokens pointer and incrementing both the line of input and the tokens pointer. And then I'm incrementing the length of the current token by dereferencing and incrementing the data at the length pointer. So the length of the current token is pointed to by the token's length pointer. It points to the tokens length array. So the first token will be the first position in the array. So the length of the first token is the value at that first position. That's why I'm incrementing this by dereferencing it first instead of just doing this. Assuming it's valid, we're going to the next token by incrementing the token count, because this is all for one. After we skipped white space, we get the current thing. This is a while loop. So after they entered in the alphanumeric token, we're going to the next token. Incrementing the counts, pointing to the next token in the tokens array, which each token right now is only up to 10 characters long. So I'm adding the current number that we have times 10. Oh, we're going to the next one. So if we entered in like dir, it would just print the directory. If we entered in like delete editor, that would be 2 tokens. So after this finds delete, it needs to go to editor. Editor is going to be stored within the next position in the tokens array, but we're going to pad out the first one to 10. So not really, we're not going to pad it out, but we'll say it's up to 10 long. So the second position in the tokens array would be 10 after the first position. So I'm adding 10 to the count. If it's the first one, I think it's 0 based though. So the second token would be 1. So it would be 1 times 10. So it would add 10 to the start of the array. That's where we want to point to. So the next position in the length array, again, we're going to increment for that. That's a pretty short, basic, little naive, little crappy tokenizer. So if we got all the tokens, we want to see if they entered in a command or a file to run or something. So I'm going to check the commands first, which I'm doing this badly. I don't have any string functions available right now because I haven't made them. So I don't have string compare or anything. So again, I'm checking basically in a for loop, basically 0 to the length of the command we're entering. So if they entered in dir, that would be 3 characters and they would each be dir. So that's all I'm checking here. The length, the token's length would probably be, it's either 2 or 3. So I think it'd be 2 because it's 0 based. So dir would be 0 for d, 1 for I, 2 for r. So I'm checking up to the token's length, which if they entered in dir it'd be 2. So 0, 1, and 2, checking if the letter in the tokens array equals the letter in the command. If it equals d and I and r, then this will be true. Then index will equal the token length. If it's not equal, we'll go and check the next one. So this is bad and verbose. I don't have string compare. So, you know, oh well. But if they entered in dir, we're going to print the file table. I'll go to that, call that function. If they entered in reboot, we're going to reboot by jumping to the reset vector, which is at ffff0 or ffff offset 0. This is, again, AT&T syntax, so jump long. Put in the hex constant, a comma for the offset, and then the next constant. She doesn't like it, but there's a cat. Look at the camera. She doesn't like it. Sorry. I do gotta sit down again though. I think I made her a little mad. That's okay. I don't know how to hold animals. I was never taught. They all they're all squirrely and weird and slick. So print reg is print registers. So if they put in prtreg, we're gonna print the registers. This is self-explanatory. That just goes back. I don't need to put that there. That comments. If they put in graphics test, eventually this will have a graphics test. Right now it just does what reboot does and goes to the reset vector. So that's okay. If they didn't enter it in HLT, we're going to halt the CPU, which is mainly for debugging, just to make sure this works. But this is kind of a useless command pretty much because we have shutdown. If the user put in CLS, that is the clear screen command. So I clear the screen and I move the cursor back to the top left. If they put in shutdown, then for QEMU specifically, I'm writing the word 2000 to the port 604, both in hex, writing out 20604, and that shuts down QEMU, just a specific thing. Box also has a sort of shutdown command, but I don't have that in here, and I don't know how to check if we're using one or the other. Probably some memory byte that I can check somewhere, but not doing that. If they put in DEL for delete, then we need to see what file they deleted and pass that on to delete file. So file name is the second token in the array, which is offset by 10 from the first token, since each one is 10 character max. So I'm pointing to that, and I'm filling out the data at that pointer to the token file name 1, variable, and then I'm passing that on, delete file. So token file name 1, and then the length of that at position 1, because it's 0 based inside this array. If it didn't work, then I need to put an error, but assuming it did work, I'm printing a new line and going back to the next command that the user wants to enter. And then if they press dir, they can see what file they deleted if it worked. It'll have free space. Okay, if they didn't want to delete, but they wanted to rename, we need two file names for that. So 3 overall tokens after ren for the first one. So doing what I did up above, getting 10, and then offsetting from 10 in the array, doing it a little bit differently from delete, which is dereferencing and incrementing. This one I'm just offsetting from 10. Putting that into file name 1, and then offsetting from 20 for the third token in the array. Token's length 2 here. Putting that into file name 2, and then passing in file name 1, the length of that, file name 2, the length of that file name. If it worked, we're going to print a new line. If it didn't, I'm not printing an error yet. So that's rename or delete. And we have load file. So I'm passing in what the user entered, which at this point is just going to be the file name to load, if it's a valid like program or file. So if it's a valid one and we want to load it, I'm checking by passing it to load file, the length of that assuming file or program name. I want to load it to memory address 10,000, and I'm passing something to contain the extension, text or bin or whatever. So if it did not load, I'm printing a not loaded message, moving the cursor and going back. If it did load, we're checking if it's a bin file, binary, or some other type. So if the file extension character matches the file bin character, file extension, we pass the load file, it'll be filled out from load file. If it's bin, then it matches, we're going to run the program, like if it's editor or something. It's a bin file, we're going to run to it to load it. So a more succinct version, instead of setting a name for the void pointer, function pointer thing, we can just do, the empty void pointer, void, no arguments, set to 10,000, call it with these parentheses. So this executes a just initialized blank void function pointer at memory location 10,000, which is where it was loaded up here if it was loaded correctly. And then that will hopefully eventually return to the kernel. If it does, we'll clear the screen, go back to the top, and then continue. Otherwise, I could probably save the current screen data in a buffer. If I move to using a back buffer, then I'll have the data saved and I can reload it here. Otherwise, right now I'm just clearing the screen. So I might do that. Let's do, just for a note for the future. Yeah, I think that makes sense. So, okay. If they didn't press a binary file, but they did a text file, we want to write that file to the screen. I'll probably put this behind a command. It's another to do. Put this behind a shell command. It's not technically a shell, so I put in quotes. Put this behind a shell command like type or other. Okay, like in Windows, the TYP will write bytes to the screen. In Linux, you have concatenate, but concatenate does more than just write bytes to a screen, which is standard out in the terminal. So yeah, I might make like a type command to do this instead of just doing it implicitly, for lack of a better word. But if we're typing out a text file to screen, I'm setting up the location as a byte pointer, character pointer to 10,000, which is where it was loaded from load file. And I'm just running through and loading that to the screen. So first I'm putting a new line and then up to 512, although later I want to do more than one sector of data. So until 512, starting from 0. If it's below F, we're converting to hex. I'm not handling new lines, which is not great, but so if it's a new line and it's not a sort of hex string constant, I want to handle that. But right now I'm just assuming they're all just ASCII hex constants or whatever. So I'm printing that out to screen, converting it if needed. Otherwise, just printing the character out and incrementing the pointer to the next one. After we're done printing out the text file, I'm printing a new line to go back to the prompt. And that's all we're doing in the kernel. But that's all I got. Hopefully this explained a lot for you, although not very well, but this is the C version of the current OS. As of the end of the previous video, it was an assembly version. I fixed up some bugs in the text editor, like navigation keys and stuff. But it's still a little buggy, as you saw, but a bit less than it was, hopefully. I'll have the source code for this current C version in a Git repo, probably on SourceHut. I'll put the link in the description. And yeah, if you want to see anything specific, let me know. Otherwise, when I get back to this, I'll do graphics primitives or a font editor, or I'll fix up the editor some more, because I do want to get to the point where this is more self-hosted. And by that I mean I want to get to the point where I can edit the OS within itself, so the binary and the text files, and then make like an assembly and an editor, an assembler and an editor and compiler and stuff. More full-featured, so I can edit the OS within itself, kind of bootstrap self-host stuff. So I want to work towards that for a medium-term goal, but other than that, maybe graphics primitives would be good for the next one, drawing lines, squares, and stuff. But my voice is dying, if you can't tell. Although my compressor seems to be peaking a lot, so I apologize if it's very crunchy. I'll try to work on that even more. Audio is very hard to figure out because it changes constantly for me for no reason. Yeah, hope you enjoyed. I really do appreciate it. I got a bunch of, people watching lately. It seems like not a ton, but more than I used to. So very thankful for that. And I'll see you on the next one. Yeah.